Well, good morning. Good morning. Good, everyone's talking before we start. That's a good sign. Welcome to the Bragg Exchange 2026. And it's really great to see everyone here for what I think will be a really exciting and interesting 2 days of worth of talk. My role here is just to say welcome to you and do the slightly boring bits at the start we need to do, and then we can get on with the more exciting bits, which is hearing about research and innovation. Before we start, a couple of quick thank yous to Space Hub Yorkshire, the Royal Society of Chemistry, who are sponsoring the event, and also the Royce Institute, who we are part of. And it is a particular pleasure today to have 3 representatives from EPSRC with us. Please do go and talk to them all the way through the day. Katie is going to give a talk in a moment or two. We've also got Sachkin and Shinatra with us. Please do explain what you're doing to them at posters in really clear ways about why it's important what you're doing. It's a pleasure also, Alex. Could you give a wave, Alex, at the front there from the West Yorkshire Combined Authority? Good to have you with us today. And also Stuart Kinley from the Royce, away from Stuart, who is the CTO of Royce, I think, if I've got the title right. I have got it right. That's excellent news. Okay. So I just wanted, before we start, just to introduce the team who are sorting this event out and have sorted the event out. There have been some changes to last year. If you remember last year, we said goodbye to Andy, who's moved on to other things, and now welcome Claire as our new centre manager. Claire is at the front here, so welcome to Claire. And also welcome to Faye, who's joined us as Communications Engagement Officer, and Faye is at the front here. So things about the centre, things about engagement, those are your 2 contacts. And then Steph, Lucy, Helen have stayed from last year. And a particular thank you for Helen, who has done almost lots and lots of the organisation for this event. We'll say more later, but thank you to Helen. Okay, so the things I have to say is we do not have any fire alarms planned during this event, and I hope there won't be any fire alarms, but if so, leave through the doors and go to the main entrance and the grassed area, which will be very muddy, outside the Esther Simpson building. And similarly, if you have anything about first aid, then contact someone here, and particularly the Bragg Centre team you've just seen. So the practical details, I said I did the boring bit. The toilets are just outside and to the right. Half of you tried to go into the toilets rather than the lecture theatre, but that's where they are, so nice and close. The talks will all be here, and then just as last year, the posters at lunch and reception will be in the refectory just up the road, 3 or 4 minutes up the road. We have about 80 posters up there, so please do go round and see the posters during lunch and the reception. Okay, this is being live broadcast. There's a camera at the back, so this is just to make you aware. You can see it, and welcome to everyone joining online at the moment. We hope you as well have a really enjoyable experience. I don't really understand these bits, but for those of you that do things with LinkedIn and other social media, please do advertise and promote the event. Really would welcome that. So please do say how much you're enjoying being here. There's a right way of answering that question. Okay, so the agenda is digital. I'm going to leave this on for a second. So the agenda can be found with that QR code. You should have had it circulated, but that's where the agenda can be found. I'm going to give 10 seconds for people to get their cameras out and do what they need to do. Mostly the EAB, I think, who have had it fully in paper form, I think, or whatever. Okay. And then on the back of your name slip, there's a poster voting slip. So the idea is during the poster session, you can vote for your favourite poster. Please do that. You get a go. That is the magic thing to put a number on for your favourite poster. And then on the right-hand side, we'd like some feedback from Bragg Centre members, not just about this, not just about the event, but the Bragg Centre in general. So we really would appreciate if you, at some point you could use that QR code to give feedback about the Bragg Centre over the last year, because it's only from hearing from you that we actually know what we can do differently, what you'd like to see. So please do use the QR code and tell us what you're doing. And the university also likes to see a big response from the community saying what the Bragg Centre has done and to evaluate it. Okay, so that was the bits that I had to do at the start. Claire, is there anything I've missed from that? No? Excellent, I've done my job. That is really encouraging. Okay, so I think I'm now able to get on to the main part of it, and starting off, it's a real pleasure to welcome Katie Blaney today. Katie and I have known each other for a number of years, which we're not counting. And Katie is Deputy Director for Science in EPSRC and responsible for strategic leadership across advanced materials, mathematical sciences and physical sciences. So all of you in here, please do try and chat to Katie today, but not just to say things which you don't like, say things you do like about EPSRC. So Katie, a real warm welcome, and over to you.
Okay, thanks Edmund, and hopefully everyone can hear me, which means I've switched on correctly, which is the first step done. So thanks for the introduction. I'm Katie Blaney, Deputy Director for Science at EPSRC, and joined, as Edmund said, by a couple of my colleagues today. Please do come and talk to us. You're welcome to give us feedback on things that you don't like about EPSRC, but as Edmund said, the things we do well are great to hear as well, and also hearing about your stories, why what you're doing is interesting, why you think we should fund it, what might be the hot new topic as well would be really great to hear from you all. I was asked to just give a bit of an overview about advanced materials at EPSRC, so I'll just run through a few slides on that. So advanced materials and our aim around this, so quite a long paragraph, but essentially we're talking about convening, catalysing and investing in a multidisciplinary community, and we talk about there being a diverse and inclusive research and innovation system that connects discovery to long-term challenges. I'll let you read the whole paragraph yourself, but I think the two areas I'd pick up there which are really interesting to me for advanced materials is the fact that it is multidisciplinary. This is an area that touches a huge amount of the research base, and there are also long-term challenges that go right from the discovery end, right from this kind of fundamental, creative, novel ideas, all the way through to the innovation space. So it's a really long pipeline of research that we see in this area. The advanced materials team is what I like to think of as small but perfectly formed. Alex Broomsgrove is head of advanced materials, and he'll be known to most of you, I would have expect. And then Chinatra here today, just at the front, give her a wave, and Sechin midway through, work alongside Alex, along with another colleague, Layla. There's a really strong overlap, actually, with that team with physical sciences, and so we do resource the team out of physical sciences sometimes as well. But the key thing is that EPSRC, as part of UKRI, is seen as a key partner within the UK materials community. We feel we play a leadership role in scoping, developing and championing materials research. That involves working a lot across a large range of key stakeholders, building relationships with them. So, all the way from internally, our colleagues across UKRI, but academia, charities, NGOs, business, learned societies, advice streams. We try and build our knowledge from that kind of huge variety of thought across the landscape. And that's really why we're inviting you to speak to us today. We're really interested to hear your views. What you tell us shapes what we do. It really is a kind of a two-way partnership in that sense. So we've got a very small number of people doing a huge breadth of work. And what we're interested in the places where new materials would deliver social, economic or other impact. We're interested in community and skills development across materials communities. So we're interested in what those skills are. We're also interested in what skills you need. Where are there gaps? Whereas the UK may be falling short, is it? Or are we internationally leading? Any barriers or challenges you find to building and delivering both the mission research, so like what you'll see in the sort of government priorities, or the more curiosity-driven. And we're also, as I said, really interested in new and emerging areas and technologies, particularly where they might need support or intervention to help them develop. Some of you may be aware UKRI had a new CEO start with us a few months ago, back in August. And as a result, as you probably would expect with this change in leadership, we have a revised mission as an organisation. It's very short and snappy, hopefully easy to remember. UKRI's mission is to advance knowledge, improve lives, and drive growth. And I think what you'll realise there is that advanced materials has a huge role to play in all aspects of that mission. It's a really key part of the portfolio that we have. It doesn't mean that anything that EPSRC is planning to do in the immediate sense has changed. Our approach has been what you can see on this slide for a while now, and really it's around 3 key points. So future-proof the STEM workforce for the productivity of UK PLC, to build a sustainable and vibrant national capability in research and infrastructure for science-driven growth, and to catalyse research and innovation the UK needs in critical technologies, net zero and the government missions. And we think that this really fits well into UKRI's mission and kind of gives us a really strong set of objectives to be working towards. So just to give a sense of what the advanced materials portfolio looks like for EPSRC, with a caveat that these figures are out of date, I'm afraid. We've not been able to pull sort of up-to-date figures from the system before this particular talk. But it really is just an illustration of the size and the breadth of the portfolio. And what I would say is that the investments that we see here do cut across all areas of EPSRC research, so ICT, engineering, physical sciences, various different parts of the career stage, so fellowships, students, more established academics. We obviously have the Henry Royce Institute, and then we also have some key infrastructure as well. And a lot of the research not only sits within the EPSRC space, but it also spans out across councils. So it's a really, really broad, really vibrant community. I mentioned the Royce, obviously the key investment in the materials space for EPSRC. This was announced in 2015. And it enabled access to over £200 million worth of facilities, and the design was about there being a focal point for UK's world-leading excellence in advanced materials research. The investment's now reached over 350 million, and I'm sure many of you know how it works in enabling academics industry to have access to world-class research capabilities. It's a hub-and-spoke model, so there's facilities and expertise across a range of regions across the UK. It's not all just concentrated in one space. And they work for the community through a range of activities and programmes and support translational activity as well. So a really kind of large investment in materials and a sort of, I guess, a bit different to funding of grants. This is about enabling access and research translation. I should probably mention the industrial strategy as well. So this is published on the 23rd of June last year. Where there are 8 sectors identified for growth, with sector plans detailing subsector priorities. You can't see the word materials on this slide. That's because it falls under advanced manufacturing. So it is there. It's a subheading as part of the advanced manufacturing section of the industrial strategy. And really there's a focus there on translation of advanced materials discoveries and a commitment as well to a national materials innovation programme. So if you're looking for further reading, then I recommend the industrial strategy is a good document to look at. We also have the National Materials Innovation Strategy with various opportunity themes as well, again, representing community needs. So hopefully there's a few areas up there that resonate with you and are relevant to the work that you're doing. And really in the advanced materials team at EPSRC, what our role is to take these larger sort of government level documents and to think about what the needs are of the research base in order to ensure that we can feed into those priorities and that we've got a capability within the UK in order to address some of the key challenges. So we kind of revert back normally to a strategic framework that we've developed. So materials with sustainable futures obviously being something that we want to develop with cross-cutting priorities around skills, infrastructure and impact and international. We have research priorities, as I said at the start, across the breadth, so fundamental, mission-inspired, and translational, with a little bit of space there still for those emerging technologies. And that's sort of the framework that we go back to when we're trying to think about what we want to do. These are very much still in development. These are priorities developed by the Advanced Materials team. They've been developed through community engagement and working with people. We have some focus topics. I'm not going to read through them all, but we have some focus topics. We have some that are cross-cutting, and then we also have areas as well, such as semiconductors, biomaterials, where advanced materials is not the primary lead on the theme, but there are areas of interest across EPSRC and beyond, where advanced materials have a strong role to play. So I think that's the thing with advanced materials, because it does cut across all areas. There's the priorities that the theme can have, but there's also responding to priorities of other themes and ensuring that there is a space for materials in what they're trying to do. So I would just say, just going back to this, for now, these are the areas we're focusing on, but as I say, it's still in development. So if there's anything glaringly obvious that you think is missing from this, then please do let us know. Just a kind of a snapshot of some of the things we do, just to say the figures here are combined with physical sciences. As I said at the start, advanced materials and physical sciences work very closely together as teams, but just kind of some idea of some of the numbers of things that we've done recently. So, you know, we've requested a lot of reviews. We've had panels. We've had lots of applications in community engagement. We work with centres. There's Metamaterials Hub. Co-investment with JSPS, and then we also work to influence future direction. So various areas there where we're talking to people, using those relationships again to have an impact. There is a highlight notice open at the moment if you're looking for current funding opportunities. So a highlight notice in two areas, one being advanced material solutions for critical minerals, and the other one in situ and in operando materials, metrology and characterisation. So these are responsive mode opportunities, but with a highlight just in two areas. And then I think finally from me, just a couple of engagement opportunities that are still open. So the Institute of Physics is currently working with the Metamaterials Network and DCIT and others to develop a 10-year metamaterials roadmap. So the final workshop for that is next month. So there's still opportunities to engage with that. And the advanced material, my colleagues are still working with AI on the AI Opportunities Action Plan, making the case for digital materials development. And so we'll continue to engage with the community on materials for the needs in this area. I think that's all I've got. Thank you.
Thank you very much indeed. I think we've got some time for a few questions. Do we have some questions? I've certainly got one, but I'll see if people have got questions. Oh, come on. Right, I'm going to start off with. So obviously there's a lot of work at the moment doing things with government and trying to influence government. So what as a materials community can we do to help EPSRC in influencing government for investment in materials and more generally some of those strategic priorities?
Yeah, so great question. We're really reliant on you. So we have to make the case to government for our funding. It's not a given that we get the money that we get. So every time there's a spending review, then we have to put various documents into government to make that case. And so really what we're looking to do there is work in partnership with you. We're with you on this. We want to get as much money as we can for the area, but we do need to be able to demonstrate what the UK government gets back for their investment that they're putting in. So where you have particular stories that you're able to tell, these sometimes are short-term stories, but they're often quite long-term, and they're really interesting because they show that what sustained investment in an area can do. So anything you've got where you can tell us why your area is interesting, why it demonstrates, delivers growth for the UK, and why not funding materials science would have an impact on the capability within the UK, we're always really interested to hear about. So please do come and find us and talk to us about it.
Down, Stuart first.
I just wondered if there's anything we could do as a community for the foundation industries. So a lot of the priorities are sort of further downstream, and I'm thinking the chemicals industry because the precursors to materials, and it's quite a hot topic at the moment about the challenges that are faced in the UK. As a community, is there anything that we can be doing that feeds into future plans for UKRI and EPSRC?
I think it's not necessarily specific to, I think all areas. If there's a story to tell, if there's a real reason why, we need to keep investing in that, or if there's particular gaps in the pipeline that are preventing translation, or there's not enough skills, there isn't the right infrastructure, all these things are really useful to understand, to kind of form a picture that then feeds into. So, for example, we've got the government priorities, we understand, their plans under the industrial strategy, but are there barriers to them be able to deliver on that? And are there investments we might need to be able to fit into that? So yes, absolutely for that area, but other areas as well. It's not necessarily limited to that. We're just trying to build a picture to understand fully what the system looks like and kind of where those challenges might be.
Chris.
Hi, Katie. I wanted to ask a little bit more about how materials fits into the industrial strategy, because I think you said it was under the heading of advanced manufacturing, but it'd be quite easy to make a case that it underpins nearly all of the others, things like clean energy, defence, digital, life sciences. So I'd be a little bit worried if those areas didn't think materials were important.
Yeah, and I think they do. I think it has to go somewhere. There has to be a heading somewhere, and it happens to have slotted in advanced manufacturing. I think the team work quite hard to ensure that materials is represented across the other areas. And when we talk about the government priorities and the delivery of funding, this is all happening within UKRI. So we do work cross-council to ensure that that there's understanding. It's not just in materials, other areas as well, where we have to kind of be very mindful of the contribution those disciplines make to those areas. So yeah, we're very conscious of that. Work really hard to make sure that there's representation, ensure that colleagues know what the challenges are. In a way, I think materials is in a good space because it's understood that it cuts across all areas. We have other parts of EPSRC where it's less known what contributions might be made to various areas. But yeah, I think it's a case that the heading has to go somewhere, and that's where it's ended. But it certainly that's where it's ended up. It certainly doesn't mean it's only there.
Now, I will ask one more question. So you showed the vast number of peer review requests you have. So I guess I know the answer to this, which is how easy it is to get those reviewers, but also if people are interested in reviewing, what should they do, and who are you looking for as reviewers in the material space generally?
Yeah, so we're looking for anyone who's an active in the material space. You don't have to be based at university. You could be based in a business as well. If you're interested in peer reviewing, please do speak to us. We do really struggle to get reviewers on grants. It really slows the time down. It's probably the longest time frame we have. So if you've ever sat there thinking EPSRC is taking ages to process my grant, the likelihood is it's because we're waiting to get even 3 reviewers. We can often go 15 to 20 people just to secure those 3. We appreciate people are busy. If you get a review request and you can't do it, please let us know as soon as you can, because we're not able to search for other people until a sort of a 3-week time frame has lapsed. So that can delay us quite a bit. So if you can't do it, please say you can't. If you can suggest someone, that's really great. And I always promise that I won't tell them that you suggested them. We'll just approach them. But yeah, please to review for us. And if you're interested in reviewing, please do. I don't think I've ever met anyone who hasn't told me that getting involved with peer review, particularly at an early career stage, really helped them understand how others write their grants, what a successful grant looks like, and can kind of really give a really good insight into how the research councils operate.
I think I agree with that. I mean, peer reviewing and also being on a panel is a great way of really understanding the process. Yeah. So I'd encourage people. Rick.
Just on the back of that, just like we are in the university facing challenges with AI-generated material, Are the research councils struggling with AI-generated grant proposals at all?
So we do have a framework in place, and I'm struggling to remember off the top of my head the exact wording of that, but we do have a framework around AI for your Curiale, which is published on our website, that you can use. I think the key thing is, of course, not to use AI when you're reviewing, because a grant proposal is private. It shouldn't be fed into it, and also we'd like your opinion as well on the grant. But there is information on our website that you can refer to that, so please do.
Okay, thank you.
Any further questions or comments? We're going to warm up during the day, but Katie, thank you very much. So a couple of things to finish with. Things that you think should feed into the materials landscape. You've got plenty of ways of doing that. Firstly, the Bragg Centre team can feed those in. We've got the Royce Institute, which is very much feeding in ideas to EPSRC, to government. So please, if you have ideas or thoughts about the materials landscape, do let someone know. Don't just thinking about them. And if you have good stories, we've heard that is important, but please also let Faye here know about them, because we can work within the Bragg Centre, from the Bragg Centre to the Royce, and from Royce through to EPSRC, and get those stories out. And it really is important that we do get those good news stories out. So Katie, thank you very much indeed. You're around all day with your colleagues, so please, you know where Katie is. She's not going to escape the rest of the day without lots of questions. So thank you very much indeed, Katie. And I think I'm now going to hand over the baton to Rick to take charge.
So welcome to the first session in the Bragg Exchange, dealing with materials characterisation. And one really quite important technique in materials characterisation is solid-state nuclear magnetic resonance, which is a really powerful tool for the determination of local chemical environments within materials. And we're really fortunate to have Professor Stephen Brown from the University of Warwick, Physics Department, who heads up the UK high-field solid-state NMR facility. And personally, although we have a large solution-state NMR capability at Leeds, particularly in Asprey, I don't think we actually use solid-state NMR enough. It's only in isolated groups, and hence this is a really good opportunity to learn more about applications in the physical and life sciences. Stephen started life as a chemist in Oxford and got his PhD there, and then he had a Humboldt Fellowship in Mainz in Germany, followed by a Marie Curie Fellowship in Lyon, and joined Warwick in 2002, and now is a chair in the Department of Physics. And Stephen's talk today will be on applications of solid-state NMR to the physical and life sciences. So, thank you, Stephen.
Thank you for the introduction, and again, I hope I've managed to switch the microphone on okay. Sounds like I have. Great. So yes, as Rick said, it's a pleasure to be here today and to tell you a bit about what solid-state NMR can do. And I'm going to present some applications from across the physical and life sciences, looking at pharmaceuticals and particularly then cellulosic materials. So to start with, just to say, you may be aware that there's recently been a substantial UKRI investment led through EPSRC, but involving other research councils for two 1.2 gigahertz NMR spectrometers, both situated in the West Midlands at the University of Warwick and the University of Birmingham, and both are actually now operational at field. There's the photo here on this side here from our opening event, where we had senior representatives from EPSRC, BBSRC and MRC all attending. So there's a great opportunity in the UK to use this state-of-the-art infrastructure, which has both solution state and solid state NMR capabilities. So we've been running hosting at Warwick, the National Research Facility for high-field solid state NMR, operational since 2010. I started off with an 850 megahertz instrument, which is still operational as a wide bore and has lots of high temperature and low temperature specialized capability. We added the 1 gigahertz in 2020 and very recently the 1.2. And essentially we can look at most things that are solid. And so this slide here gives some, but not an exclusive list of types of applications. And clearly you can see there's materials are well represented, and clearly there's also the wide range of energy materials as well, which are where solid state NMR is finding increasing application. So the method we rely on when we use solid state NMR is one called magic angle spinning, where we pack the sample into a small rotor and we spin that rotor at this so-called magic angle of 54.7, which is the root of that 3 cos squared theta minus 1 function. And if you do this magic angle spinning experiment, as I'll show in the examples, that you can approach the line widths you're used to seeing in solution state NMR. We'll still see that our lines are much broader than what people are used to seeing in solution state, but we can get information that allows us to see, get meaningful insight into the systems we're looking at. And essentially, the smaller you make the rotor, the faster it spins. And this is something I've seen in my research career. In my PhD in the 1990s, the fastest we had was a 4 millimeter rotor, outer diameter, and that could spin up to 15,000 revolutions a second. Again, it uses compressed air as a bearing, and then compressed air as a drive or dry nitrogen to spin the samples round. I was then fortunate in my first postdoc position in the Max Planck Institute for Polymer Research in Mainz to have access to the first 2.5 millimeter rotor that the company Brucker had developed. And this photo here dates it. It was actually a pre-Euro 50 Pfennig German coin. So give you some aspect of the size of the rotors. But again, that technology has rapidly moved on, and we've actually, we probably need to update, or it's actually my colleague Joseph Lewandowski's made this slide, he'll have to update it. We've actually recently taken delivery of a 0.3 millimeter rotor, and we've had it spinning at 200,000 revolutions a second. And you have to pack them in a microscope, but certainly for proton hydrogen detect experiments, that makes a big advantage. But for some experiments, you don't need to spin so fast, and then we have the bigger rotors. So we have a wide range of different rotor size for different applications of solid state NMR. But essentially, magic angle spinning is the core technique that is used in the experiment. So again, I'm going to focus on applications to organic compounds, although inorganic systems are also very important, and NMR can do lots of great stuff for those inorganic nuclei. But given today I'm going to show some results for 1H, for carbon-13, but also 14N. So it's just useful to know that NMR normally works with these spin half nuclei. In solution, the quadrupolar nuclei, that's with spin 1 and above, are usually very difficult because they relax so fast and you get broad lines. But in a solid state, we can use 14N, and I'll show an example of using that. You can do 017, it's not going to be my presentation today, but just to say the different isotopes, their natural abundance, the Larmor frequencies, they all play a role in how good a particular NMR experiment is. So for those of you who haven't seen solid state NMR spectra before or are used to seeing solution state NMR, this gives you some feel for the routine experiments we can do in solid state. So these are all examples for our standard setup sample, the amino acid alanine. And the workhorse experiment, and I'll shortly show some examples in the pharmaceutical area using carbon-13, is this so-called CP, which stands for cross-polarization. And if you spin slowly, you get narrow lines. The line widths are still a bit bigger than you get in solution state, but clearly you get three different lines for the three different carbons. You do actually get these so-called spinning sidebands either side, but essentially you've got high resolution. And again, we'll see for the early pharmaceutical examples I show that high resolution is very powerful. Now in solution, the method you'll run to is always proton NMR, and everything that makes protons great in solution causes you problems in a solid state. Nearly 100% natural abundance, they've got the highest magnetic gyrate ratio, so the biggest magnetic moments, and there's lots of them. They all couple together, and if you just record the same proton spectrum, you get basically a broad, featureless, largely meaningless hump of a signal. So I said I was fortunate during my first postdoc to have access to this 2.5 rotors that spin at 2.5 millimeter rotors that go up to 30 kilohertz. And here you could actually now, for the first time, resolve the three different proton peaks in alanine. So you've got the CH3, the CH, and the NH3. And again, I will show an example of 150 kilohertz to start seeing the resolution you get approaches what you're used to in solution. So the first example I'm going to go through is some examples, applications to pharmaceuticals, which is one of the main areas in my own research. I'm working closely with different pharmaceutical companies. This was actually work done in collaboration with AstraZeneca at the Macclesfield site. So this is looking at efavirenz, which is a HIV drug treatment, and looking at a series of 5 different co-crystals where the API, the active pharmaceutical ingredient, was crystallized with these different co-crystal formers. And even though the solid state is rigid, it's not totally rigid. There are dynamics going on. And one of NMR's strengths is it's both in solution and in a solid state, is it's very good at looking at dynamics with atomic resolution in the molecule. And that was what this work was here, and this was kind of showing that for this particular group in here, there were various different types of motion that could take place. So, in fact, a long-standing experiment that's used a lot in NMR is to analyze the so-called relaxation times. That's the time it takes to return back to equilibrium, and in particular the T1 time here. You can measure it. If you measure it at different temperatures, you get a Arrhenius-type plot, and you can then extract an activation energy. And so again, we had these 5 different compounds, different carbon spectra. Also, we could do fluorine NMR as possible. And what was interesting in this case here was that there was a pretty good correlation between what we saw in the solid state NMR with X-ray diffraction. And I'm a strong believer in using analytical science techniques together, and there is great complementarity in what you can see with diffraction methods and solid state NMR. So you actually see some correlation between the thermal ellipsoids and the activation energies extracted from the NMR dynamics. So as another example, and I mentioned we can also look at N14. So most nitrogen NMR is done with N15, which is the spin half nucleus. N14 is a spin 1 nucleus. This was some work done in collaboration with Pfizer. So on one of their, I think a lung cancer drug treatment here. And we were looking at the NH. This is a 2D experiment between nitrogen in the vertical dimension, proton in the horizontal. And you can pick out the 3 different NH groups, one here, one there, and the other one's down here. And you can actually, the difference between a spin 1 nucleus compared to a spin half nucleus is you have this so-called quadrupole interaction, here represented by the PQ value, and you can measure it by basically how much the line moves compared to N15, and you can compare it to calculation done using DFT. So linking experiment to calculation is also a big part in solid-state NMR, in the so-called NMR crystallography world, linking to DFT calculations. The other experiment we rely on a lot, and we're going to see examples in these cases for the pharmaceuticals and also in the second half of my presentation on the cellulosic materials, is a so-called double quantum experiment. And those of you who know your NMR acronyms, it's a so-called inadequate experiment in solution state. So essentially, NMR is usually all about transition from a spin up to a spin down state, the +½ to the -½ eigenstate. If you have two coupled spins, you can go from both down to both up. And that corresponds to this so-called double quantum change. Now, you can't directly observe a double quantum. It doesn't induce a current in the coil like the usual magnetization moving round in the NMR experiment. But you can follow it in a 2D experiment. And so a typical 2D experiment, if you've got this simple case of A and B, two peaks, there are three possible combinations you can have, AA, AB, and BB. And just by looking which peaks you have and which peaks you don't have, you can find out a lot about the system you're looking at. And this double quantum experiment can use the two ways in which NMR spins couple together. NMR spins couple either through bond via the J coupling, and again, I'll show you some examples in the cellulose materials using J couplings, whereas NMR spins also interact like bar magnets in those school experiments where you bring the bar magnets together. That's so-called dipolar coupling, and that's the one we're going to use in the proton experiments. So here's an example of work again. This is actually another collaboration with Pfizer on this lorlatinib, which was a lung cancer treatment. And we then do this experiment, this double quantum, single quantum on proton. And so, again, the lines are still significantly broader than what you would normally see in solution, but you can see we're picking out a large number of the different proton sites in this, this system. In particular, I draw attention to there are two different methyl groups. We've got the 23 labeled here and the 25. And this is actually a system, a so-called Z prime equals 2 system. So there's two distinct molecules in the asymmetric unit cell, so you expect two peaks in each case. And the interesting one is this C25 is actually attached to a nitrogen. And those of you who know your NMR chemical shifts will know normally that's a bit higher. It's normally about 3 or so, or a little bit higher. Whereas here we're actually seeing this particular, one of the two 25 peaks was down at 0.5 ppm. And that corresponds to something that happens in a solid state, where because the molecules are held in place, you get these ring current effects of one aromatic ring having an effect on the methyl chemical shifts of the other protons. And so because, as shown here, this one's sitting above the ring, its chemical shift is much, much lower. So you can get information from these experiments about the solid state packing, how the individual molecules pack together, for example, in different polymorphic forms of pharmaceuticals. So continuing that lorlatinib example, we can put together the three experiments we can do readily at natural abundance of organic compounds. The double quantum, single quantum, whereas I've just turned it through 90 degrees, so we have a common vertical single quantum axis. We also have a carbon proton and a nitrogen proton. Again, this system has, you look at the NH2 groups, there are, you'd expect to have 4 peaks. Again, it's Z prime equals 2, and you've got 2 hydrogens. In fact, 3 of them appear at a similar chemical shift, around 7, which is what you'd expect for something hydrogen bonding. But curiously, there's 1 peak down here at 4 ppm, and that links nicely to one of these NH2 groups, the one I've got the arrow pointing to up here, which doesn't have a hydrogen bonding partner, and hence its proton chemical shift is lower. So again, you get information where NMR is, solid state NMR is very good, is looking at these intermolecular interactions, and using solid state NMR to look at hydrogen bonding and these pi-pi interactions, CH-pi, ring current effects is something that's interested me for many years. Okay, so the final pharmaceutical application I just want to show you, and this is recent work from a current PhD student, Svetlana, working with Novartis, and this is actually work recorded this summer using a 0.5 millimeter probe. This was spinning at 150,000 revolutions a second, and you can then record a carbon proton spectrum here, which again, the resolution here and starts to look like a spectrum you'd more usually see in solution state. And again, you can also do the double quantum experiment we've seen other examples for. So it's showing, certainly for these proton detect experiments of pharmaceuticals and many other proton-carrying systems, the developments of high field and very fast magic angle spinning is opening up lots of exciting new possibilities from the technology for what we can find out about the different physical and life science systems. Okay, a short commercial break before we move on to the second half of the presentation. If you type in nmr.co.uk into your phones, you will be pleased to find out a fascinating website on national milk records. It's genuinely there, I'm not making it up. I discovered it because where University of Warwick is, it's near the National Agricultural Centre at Stoneleigh, and there was some event taking place, and I was looking through their brochure, and I came up this page saying, find out about NMR. And I thought, I must find out about NMR, and yep, everything you want to know about how to milk cows in an efficient way is on this website. So all this money, UKRI is investing in NMR, and it's all about milk records. So anyway, that was a short little diversion in the middle of the presentation. So to move on to the second half of the presentation, so the other area a lot of my research is involved with is on cellulosic materials. And in particular, it's a collaboration with Paul Dupree's group in biochemistry in Cambridge, and looking to understand plant cell walls, which obviously have lots of importance for materials as a renewable resource. And there's still lots to find out about how the different biopolymers interact within the plant cell walls. And in fact, it's a nice historical example. The very first paper, which now celebrates its 50th anniversary this year, of the now workhorse carbon-13 CPMAS experiment, one of the examples was wood. And probably the first paper which really brought magic angle spinning carbon-13 NMR to the science community's attention as a powerful new method was this work in Science in 1984, which identified two crystalline forms of cellulose, whereas the actual crystal structures were only solved in the early 2000s. So there's a huge amount of literature on applying this workhorse carbon method. You can pick out the different biopolymers in the carbon spectrum, and you can get a fair amount of information from these 1D spectra, and there's a vast literature presenting 1D carbon spectra of plant cell walls. I would just stop to pause at this moment. A large amount of this work was a colleague of ours at Warwick, Ray Dupree, who founded the Warwick Solid State NMR group, who sadly passed away this year. So these results and this paper, which we managed to publish in JACS this year, were large part due to working with his son, Paul Dupree, in Cambridge to drive this research forwards. So, as I said, the Dupree father and son team and my involvement with this collaboration, been working for a number of years, and we've published a paper very recently in JACS, where we've actually shown that how the two aspects of how the community have been interpreting these carbon spectra is subtly wrong. And actually the error, which is understandable, we'll see where it comes from, dated back to those early 1980s papers. So we saw, when we looked at the pharmaceutical, an example of a Z prime equals 2 case. It's also cellulose is a similar case. You get two different types of, you get multiple resonances here, and here we refer to these as domain 1 and domain 2. Now, the myths that currently have been working through the literature is that the domain 1 is crystalline and the domain 2 is disordered. And equally, it's usually said the domain 1 is interior to the fibril, whereas domain 2 is on the surface. And we're going to show in these results that that's not totally the correct story. And so the samples we look at, this is actually all carbon-13 labeled samples where in Paul Dupree's lab they grow like small even plants and trees in carbon-13 labeled atmosphere to enrich the samples with 100% carbon-13. And so you can actually look at and actually take the bits of grass and put them in the NMR rotor and analyze the samples. We've also can produce more high-resolution versions. And finally, so there are these two crystalline forms, one alpha and one beta, and the spectrum here in orange is actually the NMR spectra of the crystalline form. So you kind of, the reason why people say domain 1 is crystalline is its chemical shifts are the same as what you get in the same region as the crystalline form. So it's not without reason, but we'll see it's not quite correct. And in fact, the actual explanation, it's all to do with conformation around the C5-C6 bond, which, again, has been known, there's papers showing it, to actually explain what goes on between domain 1 and domain 2. So, again, the experiments we rely on are these 2D double quantum experiments. Exactly the same experiment I showed you for the pharmaceuticals, whereas those were proton using the through space dipolar coupling. Here we're using carbon-carbon using the through bond electron-mediated J couplings. And again, some work that dates back from especially Mei Hong's group in MIT have shown you can label the samples, you can get these spectra, and you can see the different sugar regions in your samples. So then you have, as I said, you have the two different domains, 1 and 2, and the power of this so-called refocused and adequate carbon experiment is you can trace your way round the carbon chain. So you've got C1 to C2, to 3, to 4, to 5, to 6. You can follow your way around. 1 to 2, 2 to 3, 3 to 4, back again to 5, and then it's 5 to 6 has got to come at some point in there. So you can, even though these spectra are quite disordered systems, you can get the information on what's going on inside them. So I said, myth number 1 was that domain 2 is disordered because its chemical shifts are not the same as the two crystalline forms that exist. However, when you look at the line shapes in the 2D experiments 2D spectra that we're recording, you can easily see that these line widths are no broader for domain 1 than domain 2. So you have the same degree of order, in inverted commas, in the two forms, the two domains. So all of this work that talks about a crystallinity index is not valid. So the other statement that's often said is to try and understand the results. There's lots of debate as to whether in the inner fibril you have 1 beta or 1 alpha. And just to say, you can do diffraction obviously on these systems, but because they're so thin fibrils, you get pretty broad diffraction peaks, so you don't get so much information. But what you really see is this work clearly shows that the only peaks that are present, so these orange and purple circles, are the crystalline chemical shifts, and you see the orange ones match up perfectly, whereas the purple ones don't. So it's convincing evidence there's only I beta present. The other experiment we rely on is we can do experiments to only see or enhance the signals that are close to water. Obviously, a living system it's not dry, there's kind of water in it. And you find that if you look at there are 3 different peaks for domain 1, the A, B, and C, whereas, and actually this slide here, the actual chemical shifts of A and C correspond exactly to the I beta chemical shifts, whereas the B peak is the one that's enhanced in the water edited. So that suggests that even though it's in domain 1, what's often called the interior, it's likely to be on the surface of the microfibril. So the simple statement that domain 1 is interior, domain 2 is surface, largely true. A and C are interior, domain 2 is surface, but we have strong evidence that the actual B peak is also surface, and the difference corresponds to its conformation. And if you then assume that's the case, and you then go and calculate what your ratio is of interior to surface, you get a ratio of 1 to 2. And there are lots of models in the literature as to how the plant cellulose fibril forms. largely based on some structural biology evidence for the cellulose synphase complex, and also like microscopy to see how wide they are. And so the current probably winner in the literature is an 18-chain one. And there are then, if you have a 1:2 ratio of the interior compared to the surface ones, that's consistent with some of the fibrils, the habits you can envisage in those cases. Whereas there have been previous papers which were not getting this 1:2 because it was treating B as an interior, and those were then the NMR data was totally inconsistent with these models. Whereas understanding B to be surface leads to then a kind of, the NMR is saying something else that agrees with biology and agrees with microscopy. Okay, so that brings me to the end of my presentation, and I hope I've given you a flavour of some of the things that solid-state NMR can do, using very high magnetic fields, using the fast magic angle spinning, applications I've shown about the pharmaceuticals, the plant cell walls, and again, obviously, there are many other areas that NMR has got a power to work across the physical sciences, life sciences, especially within materials. So thank you.
Thank you, Stephen. Do we have any questions from the audience? Edmund.
Thank you. Tell you about the facility. So can I just ask, if people are interested in using the facility, what are the mechanisms, and particularly since there seems a lot of interpretation then to go with the data, both the doing the experiment and analysing the data for someone who's coming from outside the field, what do they do, how do they go about talking to you?
No, it's a very good question as to how, if you've seen this or if you've seen other papers about what solid-state NMR could do and you're interested in doing some experiments, yeah, we're very keen to have new users come and work with us. We have a facility management team. We offer test days where you can send the samples in, or you can come and work with the facility managers just to try out whether for your particular system the experiments are going to tell you anything novel. And certainly, yeah, for new users, there is the support in also writing up that first paper and helping them to apply for so we do have a 6-monthly call for the formal applications to the facility. And again, for new users who are totally new to solid-state NMR, that process can help people in. So yes, if you're interested, contact me, contact the facility management team. They're all readily findable on the website. So yeah, absolutely, we're very keen to have new users. So do get in touch.
Jim.
Thank you. Yeah, thanks for that talk. You were using the line widths in the two different domains as a way of looking at the degree to which they're, well, I wouldn't say the degree to which they're ordered, but the degree to which the order is different in the two of them. And I guess I was a bit surprised at that. I would have thought that was really a measure of the homogeneity of the environment of that particular bond. And I guess the sort of the ultimate case of that is solution, where everything is disordered, but the line widths are very narrow. The environments are completely homogeneous. So how do you differentiate then between homogeneity and order?
Yeah, there's a lot to that question. So there's obviously going to be so-called static disorder and dynamic disorder. So in solution, you have total dynamics and you narrow the lines. So yeah, so in a solid state we can look at gel samples, and you can again see you get narrower peaks for the gel type phase. And there are experiments that, essentially these experiments are recorded using this cross-polarization experiment, and that relies on there being something rigid still in there. So again, we can do experiments using so-called direct polarization, where you actually just do a single pulse. And again, that will pick out everything, including the more mobile parts. So this experiment has already chosen the more rigid parts. I guess the particular case we're making in this work here is that the field says that domain 2 is disordered, in which case you would expect much broader lines compared to narrower lines. The lines here are, the line widths are the same. Now, our argument, it's static disorder, at least on the timescale of the NMR experiment, and it's the range of environments is giving you, the peaks are broader than in the crystalline forms. So yeah, there's a lot of complexity in your question. I don't know whether I've touched the surface of answering it, but I'll happily discuss afterwards where you're coming from. It's an interesting question.
I'm pedestrian in NMR, so
No,
I'll need more instruction.
I'll happily discuss further afterwards, yeah.
Please.
Thanks very much. Very nice presentation. If I could ask you to speculate, if we gave you a crystal ball and you could spin it at 200 kilohertz, in 10 years, outside the healthcare space, where do you see big breakthroughs coming in material science for high-field solid-state NMR? I can see the question, but...
Yeah, so, well, it's interesting to actually see when you hear... So obviously, Brooker have got an interest in selling these big magnets. They've invested huge amounts of money in the superconducting technologies, and they want to sell more of the 1.2 gigahertz. They actually said they've actually made 1.3, and they believe they can make 1.5. They've actually, interestingly, switched to actually saying the future for them is materials. Even though their name is Brooker Biospin and they've been well bought into the life sciences, Patrick Vickers, who heads up their magnet division, has been saying the future is materials. Clearly, in the UK, you've got big Faraday area, battery materials, Claire Gray's group, Cambridge, and sort of around that area. So it's actually the solid-state NMR, the high field, the materials applications, and again, I've only touched the surface of the materials in this presentation. There's a whole huge area of inorganic materials where there's a large amount of work going on in the UK. It was right back at the start. Sharon Ashbrook's Russell Morris up in St Andrews, Fred Blanc and others in Liverpool. So I've got John Provis with the cements. So kind of, it's actually, you listen to Brooker, even though in this year or so, they're saying materials are the area, or the life science is still important. There's still stuff in that area, but that's where they're seeing the future as to what you can do with the very high field NMR. So there's that. I'm not just saying that because I'm here at the Bragg Institute either. It's actually if you hear Patrick Vickers from Brooker or the Brooker leaders speak, you'll hear them say similar things.
I think that's a good point to end on, and I thank Stephen a lot for introducing the technique to the Bragg Centre members, and I'd really encourage you to reach out and discuss potential experiments with the National Research Facility, so you can go to their website to see that. Okay, thank you, Stephen.
Okay.
Okay, our next speaker, who's right over on my left, is Dr. Anu Pallipurath from my school, the School of Chemical and Process Engineering. Anu's a Royal Society Olga Kennard Research Fellow, in which she's developing new principles for the design of metastable therapeutics, using various scattering methods. Anu's a chemist by training, received a PhD from the University of Cambridge, and spent time in Ireland, in Galway and Bath before joining Leeds in 2018. So Anu, thank you.
Thank you for the introduction, Rick. So my talk is going to be sort of bits and pieces of things that I've done and how I'm going to bring them together as part of my fellowship. So hence the sort of WIG title, where I'm saying I'm probing solutions and surfaces, trying to bring together the few streams that I'm working on. So to have metastable therapeutics, so COVID has shown us that we can kind of stabilize things at minus 80 degrees, thaw them out, and then use them in solution state. So when I wrote my fellowship, I was thinking, why is it that we're having everything in a solid state? The kind of answer would be compliance. in terms of medication, compliance and stability, etc. But COVID showed us that we can keep things stable in a solution state and deliver drugs in the state where most of our body is. It's fluid rather than, it's only the skeletal structure that's actually rigid, right? So to understand that, we need to understand how things crystallize and hopefully understand how to keep them from just not crystallizing enough to then deliver it to the body. So that was the thinking. And to do that, we need to understand this region here. So that's where you have the molecules in solution and how they compete with the solvent and itself and anything else in the solution, and before they turn into a solid form. And in the solid form, again, we have different structures based on interacting, how the interaction energies change, etc. So we can use a technique called X-ray phase contrast imaging to visualize what's the dynamics in solution and use X-ray scattering to understand local structure and use a more traditional vibrational spectroscopy to understand conformational changes and how bonds interact when you have torsions where scattering gives you similar patterns in different conformations. So for that, we can do that now because we've got high energy X-rays in terms from synchrotron sources. So if you've not seen a synchrotron before, it's one of these donut ring type facilities where electrons are generated, come over here, generated in this bit here, and they're injected into this little ring, and magnets kind of amplify them. And then they're further injected into another bigger ring, which is this outer ring. And they're accelerated so much that by the time it hits your sample, it's 1 million times brighter than your lab source. So that makes it possible for people like me to study organic solutions, because what we're looking at is an organic molecule in an organic solvent, and so the contrast there is very low. So the first technique I want to tell you about is called X-ray pair distribution function analysis, which is literally looking at how, if you consider this one atom, where are the other atoms around it? So from your spectroscopy, you can get bonding information. So how is A and B bonded together? But what this technique allows you, tells you, is how does that behave based on where atom C is, for example. So it helps get towards the many-body problem, as the physicists would call it. So this area here, so this is literally the distances and the interactions between the atoms. This is your bonding information that will correlate to spectroscopy. And this is the long-range order, so what information you would get from a solid state, so a crystal, for example, once you have things ordering in a pattern. So what I'm interested is in this interaction here, the dynamics in the local structure. The beamline looks something like this, nothing fancy like what we have in the Bragg, everything's open, and the detector's there. And this is sort of a 2020 version. I'm going there next week since then. So I'm excited to see what new developments they've made. Our reactor looks something like this, and you have an X-ray transparent tube in front of the detector there. And so we collect crystallization information, or we do cooling crystallization. And so this is an example of imidazole, where we cooled the solution from 30 degrees all the way down to 14, 15. And we also had, if you go back, a laser pointing at the reactor just to measure the turbidity, which is where you say, okay, now the laser intensity has dropped. That means we've got solid particles in the solution. And interestingly, we correlated that with the X-ray scattering. And I've divided the data that we got into different sections, because there was a point where when Leila was running this experiment, the laser intensity started dropping, but then obviously we couldn't see any crystals. And then once the crystals were formed, the intensity dropped a lot, and the temperature increased, which indicated crystallization had happened. So what we can see here is looking at the interactions between imidazole and water, and imidazole and imidazole. So the red bits here are where you'd find water. Just to say, to arrive at that picture there, we had to optimize a box of molecules and then fit the scattering from the box of molecules to refine it against the experimental data. So there's a lot of behind-the-scenes work that I'm not showing you here. And what you can see is that anything here at 90 degrees, that's random, which you would expect of a solution. If you don't see it, then there's something wrong. Then you can start seeing the next level of interactions. So you have the ring of water. So that would be hydrogen bonding. Similarly, there you would expect hydrogen bonding there. What you can see is the hydrogen bonding is sort of chemically expected, right? But this carbon atom here has got both water molecules. So I think in this one it's inverted here. So I'll take that one, for example. The carbon here has got both imidazole and water interacting with it, which now is which is called the T interaction. So you've got the pi-pi interactions, which are these blobs, and then the hydrogen bonding that's happening there. And as your densification happens, the range of the pi-pi interaction increases. So you can see the molecules are starting to align themselves, which is interesting to see. I wouldn't take much of that because we're kind of, at that point, we've got crystals and solutions, and we're limited by the software at the minute because one needs mathematical summation while solvation does not need that. So we're kind of constrained by that, but hopefully we will get there soon. So the next technique that we looked at was X-ray phase contrast imaging. So here we're looking at the solution or crystallization of the molecule lovastatin. So imidazole dissolved in water very well, so it was easy or easier to study. But lovastatin is not very soluble. For example, you get, if you consider a box of 1,000 molecules of solvent and lovastatin, only 7 of them are lovastatin. The rest is all solvent. So that's the level of solubility we're dealing with. We looked at the crystallization using X-ray phase contrast imaging. So it's like a radiograph, but what we're looking at here is how the X-rays phases shifts when it passes through an interface. Traditionally, when you look at crystallography, you kind of chuck that information out. You look at just the absorbance, the intensity change. Here we're looking at how the waves are misaligned, essentially. And some clever mathematician wrote the software that we could use. And while looking at the video, again, it was still just grayscale. And then in a discussion with our RSC, Joanna Lang, she had a brilliant idea where she said, oh, why not use Euler video magnification, which is a video processing technique they use for facial recognition. And so we tried using that, and suddenly all these new features started appearing. So we could see film growth on the reactor. We can see things starting to oil out. Mind you, you can see some of this if in other molecules with naked eye when the concentration is high enough. But the case here, as in most drug molecules, the solubility is quite low. So it was fascinating to see that that's how it works. But again, when we go back to the previous situation, we're pointing and shooting there. And this is, again, a 2 millimeter by 2 millimeter field of view. All of this is happening simultaneously. So how can we combine that visualization with getting the scattering information from different places? That is one of the challenges I'm hoping to address during my fellowship. So then to add a vibrational spectroscopy, I'll speed up here. We are using Raman to look at how the polymorphic changes happen during crystallization. So this is work I did with Karen Robertson in Nottingham, while both of us were in Bath. Again, context is I'm trying to put this together with the other techniques. And here we're looking at succinic acid, and succinic acid crystallizes in the beta form, but it always has an alpha impurity. And what we could see using Raman is that it starts off in the beta form, and then you slowly start getting alpha crystallizing in with it. So once you've got the polymorphic information, then how does that change to, how does that help with understanding the product? So this is where one of my students, Dave, was working with AstraZeneca, and we were looking at the surface of the crystal itself once it's formed, using polarized Raman, where changing the solvent changes what you see on the surface. Even though traditionally you can use attachment energies and sort of predict what you get, but when you change the solvent, and when you have large molecules, your properties change based on which functional groups are presented on the surface. So using polarized Raman, what you can do is you change the polarization of the laser, and that specifically changes the intensity of certain bands when the alignment of the functional group changes with the the polarization of the laser. So for example, if your electron cloud is pointing that way and your laser is pointed this way, that's what you're seeing here. There'll be a change in intensity. But if your electron cloud is this way and your laser propagation is this way, you wouldn't see much of a difference there, for example. So your spectra looks something like this. So there are some peaks that don't change at all, while there are others that kind of come and go when you turn the laser polarization. And this crystal is paracetamol, and your B and C are X-ray equivalent. So I use the term surface very loosely here, where to understand what's the surface, we need to be able to tell the difference between crystal facets. But using PXRD, these two crystal facets are identical because their D-spacing are identical. But then when you do sort of a surface analysis using the CCDC tool, you can see that they kind of predict groups pointing in opposite directions. And we can actually see that using polarized Raman. So the orange plot, the red one is your OH groups in paracetamol. And, well, all of them are, sorry. Red one is your 001 phase, which is the phase A there. And the green and blue are pointed slightly that way, which is the 011 and 0-11. And orthogonally, we've got the NH group. But here, what I wanted to show you is, so this is the DFT calculated polarization behavior. But you can see that there are some deviations that you see experimentally. You have spot size differences and say features on the surface, basically. If that wasn't there, I would be suspicious. And so what Dave did was he went one step further and he minimized the differences between the pure bulk data and the experimental data to then see, can we identify how the functional group lies on the surface? And for the example of paracetamol, it's not straightforward because we've got 4 molecules in the crystal structure, and it's a centrosymmetric crystal structure. So if you do an average, it kind of just cancels out. So he came up with this degree of parallelism, basically. So you're taking the cosine of the angles of the functional groups. And you can see that some of them behave, so the NH stretch on the big facet sort of behaves like the bulk, like you would expect. But NH on the sides facets are very, very different to what you would expect from the pure bulk. So this is just the beginning. We're hoping to get some more information there with AFM and other techniques to validate what we're seeing. And at this point, I'd like to thank the people I've been working with. So Gunjan was involved in the XPCI work. Bethan worked with me for the XPDF. And Swen is my mentor, my previous boss. And Phil and Dean from the Diamond Light Source. Helen, two Helens, and Mark from AstraZeneca, as well as Karen Robertson, Chick Wilson, and Lois and Pierre. And lastly, we've got Dave, who's my, now postdoc, just finished his PhD, and Jonathan, who did the DFT calculations for us, and Joanna, who was a postdoc who did some calculations for us as well. So that's me. Thank you.
Thank you, Anu. Any questions from the audience? Oh, right at the back. Yeah. Get your steps in.
Thank you very much. Really lovely talk. I was surprised to see you could do structural refinement against X-rays, because across the other side of the Rutherford Appleton Laboratory, there's the neutron scattering facility. I was wondering if you've given any consideration to using their instruments and their structural refinement to investigate some of the interactions you're seeing.
Yes, so we have a neutron beam time coming up for one of the systems that I'm working with Karen on. So neutron there, it'll be really interesting to look at the proton positions. Neutron is sort of slower than what we need to be looking at. So, crystallization is quite fast, and especially nucleation is like stochastic. So that's neutron is slower in that respect, but then it gives us a different kind of information. So something I didn't show today was sort of the use of quantum crystallography to look at the proton positions. Yeah, that in that respect, that would be very useful. It's complementary, is what I'm trying to say in my babbling.
Thank you.
Any further questions? Can I just ask one clarification? The polarized Raman, is that lab-based or?
That is lab-based, yes. Yeah. So Raman is quite versatile in the sense that you can use them as probes in process engineering, as well as more sophisticated when you have objectives and things. So this one's the one in physics that we use. And usually the process Ramans are not polarized, but we're hoping to put some ND filters and see if we can achieve that. But yeah, so this one and the work with Karen that I showed you, they are using objectives, lab-based basically. But interesting you should ask, we've got a beam time where we're trying to take one of the Ramans and do it, collect the data with X-ray scattering. So
simultaneously?
Yes.
Oh, wow. Yeah. Thank you. Can we thank Anna again, please? Okay, our final speaker is Dr. Mingwen Bai from School of Mechanical Engineering. So Mingwen has a PhD from the University of Manchester. He's been at Sheffield and Nottingham and was appointed assistant professor at Coventry before he joined Leeds in 2023. And he works with a broad applications of materials across aerospace, power plants, nuclear reactors, and he's going to tell us something about materials failure analysis using in situ scanning electron microscopy. Thank you.
Thank you, Rick. Thank you. Hi, everybody. My name is Mingwen Bai. I'm a lecturer from mechanical engineering. I'm so glad to be here. I'm also very aware that I'm probably the only thing between you and your lunch. I would try to finish everything in 10 minutes. So today I have the pleasure to talk about AI, how AI, we can use it to understand the materials failures better. And I'll take thermal barrier coatings as one example, a material that I've been studying for the past 15 years, a very special materials that can mainly made by the 3 major players in the world, 2 in the US, 1 in the UK, being Rolls-Royce. And thermal barrier coatings look simple, like a white paint on top of a turbine blade, to protect the turbine blade in the hottest section of a gas turbine engines, with a working environment with temperature over 1500 degrees C and a high pressure of 40 bars. And what conventionally this industry has been studying in the past 50 years is more like a post-mortem studying failure analysis. Take this one turbine blade as one example. What we normally do is see these areas without coatings, and we cut the sample, look at the cross-section, and then try to look for cracks at the micro scales. But it always come up into a fictional kind of story that we need to have all kinds of failure mechanisms in different ways. But which is what we always found is often too little and too late. Especially when this is so challenging, when you have a multi-layered system, where you have a ceramic top coat, and then on top of a metal, which is superalloys. And in the middle, you have an intermetallic bond coat, bonding the 2 very different materials, ceramic and metals, together. And this makes even modeling difficult, because of the very complex working environment, complex stress field. What we have found developed in the last few years is, for the first time, we have developed mechanical testing, in-situ mechanical testings of thermal barrier coatings inside our scanning electron microscopes. And that enables us to directly observe the crack initiation and crack propagation through the whole coating systems. That kind of complete story, which is always missing. And this is the work started from 2023. Also, my favorite videos that went very popular online. I got like almost 1 million views on LinkedIn. But since then, 2023, I realized I'm not really like a YouTuber, making monies from these video views. But I really want to learn from these images. These images has hidden informations, especially when we collect loads of them, a whole time frame of these images. We want to use the power of AI to turn in-situ SEM into an intelligent failure analysis platform. And that's mainly in 3 ways, where AI for interpretation, where AI can automatically detect cracks from the SEM images. AI for speed, where we use AI to restore the fine details, to improve the resolutions in order for faster scan SEM imagings. And thirdly, we use AI for prediction, to predict failure, not only the location, but also when the failure will happen and how much lifetime we remained. And this type of AI is not just ChatGPT level of AI. It is really, we use deep learning models to identify and also distinguish these real cracks from the natural microstructure features. So for example, this is an EBPVD coating where you got these columnar gaps that looks like cracks, but they are actually beneficial features useful to relieve the thermal stress during the thermal expansion mismatch. But these large gaps, they are the real cracks. And that sometimes even confuse a materials expert. What we did, we pre-trained 10 CNN models, convolutional neural network models, on a large data set, 14 million images across more than 1,000 different classes. That including all the pictures of cracks in the wall, crack in the ceiling, crack in your phone screens. and then fine-tuned into our own case, which is the thermobaric coatings, using the 4,380 SEM images taken from our labs. Just ask the machine to make simple decisions, whether there is a crack, positive, there is a crack, or no crack at all, negative. And the accuracy we can achieve over 97%. And it not only tells whether there is a crack or not, it can identify the exact location of these cracks using heat maps. So what normally takes a human weeks to analyze through thousands of SEM images now can be completed in minutes, which is truly amazing. And secondly, if you have been using SEM before, you know there's always a trade-off between the spatial resolution and the time resolution. So if you want a high-resolution SEM imaging, you need to slow the scan speed. What we use AI here is to use AI to restore these fine details that enable us to restore the features such as these crack initiation points from the surface defects and see exactly how it propagates along the defects like pores, oxide, splat boundaries that enable us to complete the story. And also further, we can use digital image correlation to analyze these data in more details. That plotting the strain field mapping in two directions, you'll be able to see something that we can't see just simply looking at SEM images, like these crack branchings in two directions along the interface, which is very important for us. And finally, we combine the experimental data, the in-situ SEM images, DIC, with computational modelings. So we want to create a single predictive framework that can predict, that can learn from the damage, strain, stress, the complex relationship between these data, and then provide us with something like this, a prediction map. Tell us where exactly the crack will happen and when. So all in all this work was done by my superstar PhD student. Also, his PhD was sponsored by a UK company called Tech, who provided us with this special in-situ tensile stage. We also received significant support from many collaborators who provided us with samples. As you know, the more data we have, the better our AI becomes. And final word, I think this AI into in-situ SEM thing is just the beginning. In my research, I collected loads of millions of these SEM images by recording videos. And these are all valuable input data that we can learn something from it and also train into a model that we can make our AI models more accurate, more predictive. And final page, all the experiments can be done through our ROI systems. You can contact LIMAS, the microscoping center, because we got the best in-situ micro and nano mechanical testing system equipped in the plasma FIB system. And I'm very happy for any new collaborations. Thank you very much.
Thank you, Mingwen. Any questions?
Yes.
Please, Sheeta.
Thank you. That was a really interesting talk. I'm just intrigued about your predictive capabilities. Now, if you take the example of corrosion modelling, it's been 30, 40 years and we still can't predict corrosion properly. So I'm just intrigued how you're going to go from something which is seems to be a very physical process to be able to predict where, why, and how you might get the cracking.
Very difficult question. I think I only have a vision here, but then how are we going to make it happen is that we must have collaborative efforts to build this. We need someone from computer science background, material science background, and someone we can link together to get this corrosion problem solved and predicted. I hope that answered my question.
Edmund?
Yes.
So you talked about your training sets. Were they all your data, or was it data you'd acquired from the literature? And if it was data from the literature, did the data have enough information for you to be able to use it usefully as a training set?
Very good question. The 4,000 SEM images are from our own labs, but obviously made from the same SEM equipment. But the more data we send, all varieties of like different SEMs, different working conditions, that would fulfill the whole, complete the whole kind of training data set. Obviously, the more the better. That's all I know so far. Does that answer your question? Yeah.
Any final questions before we break? Please.
Yeah, just linked to Edmund question that you have, lots of collected images from your experiment. Just wondering whether they are available, for the wider researchers as well, research community.
Collaborating with wider range.
I mean, your database set.
Is your data available for wider research?
Do you make it available?
Yes. All open data source. Yes.
That's perfect.
Thank you. So can we thank all the speakers,
right,
including Mingwen?
Thank you very much, everyone, for the first session speakers. And you'll be all relieved to hear it's time for lunch. So please head over to the refectory, have a look at everybody's posters, and grab something to eat. There'll be some members of our team at the front and the back of the group to help you find your way if you don't know where you are going. See you for session 2 this afternoon.
I'm ready.
Okay, welcome back, everyone. My name's Chris Marrows. I'm the head of condensed matter physics in the School of Physics and Astronomy, and I'm also the theme lead in the Bragg Centre for Electronic and Photonic Materials, and that's why I have the pleasure of chairing this session today on that class of research. So I'm delighted to say our first speaker today is Professor Rob Hicken from the University of Exeter, who has been actually a long-time collaborator on and off down the years. His research interests lie in magnetic materials, spintronics, photonics, a focus on ultra-fast and high-frequency processes, and his research is directly relevant to data storage, but also new paradigms for data processing, such as neuromorphic computing and magnetic-based logic. As a consequence of this, Rob is the lead of the EPSRC-funded AFMNet, a multidisciplinary community for studying antiferromagnetic materials and ultra-fast processes, and I'm sure we'll hear a little bit about that in a moment. So his talk this afternoon is titled Opportunities for Electrical and Optical Control of Magnetic Order in Antiferromagnetic and van der Waals Bonded Materials. So please, Rob.
Thank you very much for the kind introduction. Can you hear me at the back? Yeah, it's good. Okay. I'm going backwards, okay. There's my pointer as well. All right, well, thank you. Chris has said a lot of nice things, which I was planning to tell you myself, so you saved me the trouble. I have a rather long title, and that's because I wanted to fit in with the theme of electronic and photonic materials. What I'm actually going to tell you about is how we can manipulate magnetic materials, both with electricity and light. And I'm going to focus on two topical types of magnetic material, antiferromagnets and van der Waals bonded materials. Okay, so I was planning to introduce myself. That's been largely done. And then I was going to tell you about antiferromagnetism, some recent advances, and why it's suddenly of interest again. And I'm going to tell you about some of the work we've done in Exeter, actually on some very well-known antiferromagnets, cobalt oxide and nickel oxide, and yet we can still find new things to do there. And then I'm going to change gear a little bit. I'm going to talk about van der Waals bonded few layer materials, and particularly hybrid materials, and show you that we can manipulate their magnetic order optically. And then I'll draw some conclusions. So I tend to forget this, so I thought I would do it first. I just want to acknowledge all the collaborators who are involved in the work that I'll present. I noticed this morning, because I submitted my slides in advance, that I'd actually acknowledged Edinburgh twice. So that was an oversight. They did a great job, so maybe they deserve it. Okay, so about myself. So I come from a materials device physics background, and as Chris said, my particular interest is in high frequency and ultra fast processes. So if what you do with materials is relevant to information and communication technology, we know there's a drive to make everything smaller, but the flip side of that is that everything has to happen more quickly as well, such that we now need different techniques, and the techniques that I use are magnetic resonance and then time-resolved optical and X-ray probes. And that gives us access to the nanosecond to femtosecond regime, which is where, if we think about ICT today, that's where clock speeds, it's where bit rates are at the moment. And it looks like something got missed out there. I'm not sure what it was. I also wanted to tell you that I direct a facility in Exeter. This is the Exeter Time Resolved Magnetism Facility, specifically to study magnetic materials and systems, changing their state on short time scales. It was funded by EPSRC, through the strategic equipment process, and hence we run it as an external user facility. So if you see something that you like and you'd like to come and try it, then you can find us on the web there. And as Chris mentioned, I'm also the project lead of a new EPSRC funded network. So this is AFMNet, a network on antiferromagnetic materials and ultrafast magnetic processes. So the network began on the 1st of October last year. We had a kickoff meeting in early November, and our website should hopefully appear by the end of January. And when it does, then everyone in the community will have the ability to join the network. In the meantime, if you want to know more about that, probably easiest just to email me. And it seems very appropriate that I'm in Leeds because AFMNet has received a lot of support from Leeds via the Henry Royce Institute here in getting the network funded. And in fact, the Royce Institute is still providing us with some administrative support. So thank you very much to the Royce Institute. Okay, so let's talk about antiferromagnetism. So I realize that it's a broad audience and a lot of people not know much about this. So antiferromagnetism is a form of magnetic order that was proposed by Louis Néel in 1932. And at the time, he commented that he thought it was of no practical use. And to understand the reasons for this, here's an example. So this is a very well-known antiferromagnet, manganese fluoride. This is its unit cell. And there is no net magnetic moment within the unit cell. So the moment pointing down in the middle is compensated by the 8 at the corners, which are each shared with 8 other unit cells. So there's no net moment, so that means it's difficult to probe any magnetic order using most of the techniques that we use. And in fact, you have to use neutron scattering to see the magnetic order. And that usually means using big single crystals. The lack of a magnetic moment means it's also rather difficult for us to manipulate the magnetic order. Now, that's not to say that you can't induce some magnetism if you apply a field. There is a small magnetic susceptibility, but it's anisotropic. And you're better off, say, applying the field in the horizontal direction here, and that makes the magnetic moments tilt towards the field. If you really want to change things in a big way and maybe switch the magnetic moments on the 2 sublattices, then you need large fields. Typically, you need 1 to 10 Tesla to induce what's known as a spin-flop transition. So clearly, that's not very helpful when we think in terms of device function. Now, it's not quite true that effect is completely useless. In fact, there's one very significant application, which is if you stick an antiferromagnet next to a ferromagnet, then you can apply an effective field to the ferromagnet. And that effect, exchange bias, is used to bias magnetic field sensors. And that's been used in magnetic hard disk drives for a couple of decades. And in fact, exchange bias is something which has been studied extensively here in Leeds. Okay, so that was the past. What's happened recently? Well, more recently, it was realized that certain classes of antiferromagnets, and bear in mind that they're almost all compounds. There are lots and lots of different compounds that are antiferromagnetic. Those known as the altermagnets and non-collinear antiferromagnets, they can, on grounds of symmetry, exhibit additional useful effects. So if we look in momentum space, in the Brillouin zone, then it turns out that while the electrons in the first Brillouin zone have no net spin polarization, they are polarized in certain directions. So what that means is if we were to draw an electric current out of the material, say along the x-axis, then the electrons would be spin polarized. So the current would carry a net angular momentum that can exert a torque on something else. The other new properties are that if we were to place electrical contacts on one of these antiferromagnets and try to measure the Hall effect, we would see a non-zero Hall effect. So what we're doing is maybe our moments are like this, and then we flip them upside down like that, and the Hall signature changes. So that's surprising. And alongside that, you also get a magneto-optical response in some cases. So the point is that there are mechanisms now to detect antiferromagnetic order. And one can go further. One can induce electric current into an antiferromagnet. You've got to pick the right one. This is the work of Peter Wadley at Nottingham. So he's made a device here from copper manganese arsenide, injected current, and he can cause the magnetic moments to flip through an angle of 90 degrees. So in principle, that is a device that one could use to store information. So this seems like an elaboration on something we already have in the form of ferromagnets, but the advantage is that antiferromagnets have no stray magnetic field, and that means that they can be packed closer together for higher density, and also it turns out that their response to excitation is faster, and on principle we can switch them on timescales of the order of a picosecond. So it's also potentially an ultra-fast form of magnetic memory. Okay, so I want to move on to some work that we've done. I want to talk about nickel oxide and cobalt oxide, which are conventional layered antiferromagnets. What happens in nickel oxide is that the magnetic moments order in 111 planes, and when they order, you also get a strain, the so-called exchange striction. It's the order of 10 to the minus 3. And so this cube gets distorted along a 111 axis, orthogonal to the planes in which the moments order. So there are 4 such planes, and within each plane, there are 3 different ways that the moments could be aligned. So there are a total of 12 possible domains in a bulk nickel oxide crystal. If we think about cobalt oxide, it's a little bit different. Again, it has the rock salt structure. Again, it's a layered antiferromagnet. But what's different here is you'll see that there are 2 arrows on each atom, and the reason is that the orbital moment is not fully quenched in cobalt, whereas it is in nickel. And the upshot of that is that the moments order close to a cube axis, and actually that exchange striction is even larger. It's the order of 10 to the minus 2 strain. Okay, so we're not particularly interested in the bulk materials. We want thin films. So when you try and grow a thin film by deposition on a substrate, if you have an epitaxial film, the growth will also induce a large strain in the film, which modifies the magnetic anisotropy. And what that means is that the direction in the moment that the moments point in changes again. So what should happen is that you have 4 domains, and the moments should be aligned at 35 degrees to the normal. Because of the strain, actually it's more like 10 degrees. For cobalt oxide, it's simpler. There are 2 cases. They align along one of the 111 O axes. And the strain associated with the antiferromagnetic order gives you magneto-optical birefringence. And that means that we have a method to sense the antiferromagnetism optically. And there's a simple way of doing this. You put your sample in a polarizing microscope, you go close to extinction, you have an analyzer. As you set close to extinction, you go a little bit off extinction in either direction, get 2 images and take the difference. And when you do that, you get nice domain images. So this is cobalt oxide and nickel oxide. And what we're seeing here are domains, the black and white, where the antiferromagnetic moments are either along 110 or 1 bar 10. In the case of nickel oxide, what we're sensing is the projection in the plane of the film. Okay, so that's our detection mechanism for a conventional antiferromagnet. And just to give you a flavor of what we're now trying to do, we're trying to manipulate the magnetic order optically. So to do that, we have to construct a special multi-layered stack. And so what we've got here is a layer of cobalt oxide, a layer of nickel oxide, and then a layer of iron on the top. So we use this bilayer because the exchange coupling between the cobalt oxide and nickel oxide tends to pull the nickel moments more towards the plane. And then they interact again with the iron on top. And that's useful because we can apply a field and we can control the orientation of the iron, and then that drags along the nickel moments with it. And the reason we built this stack was because we wanted to excite it optically. And what happens if we excite this with an ultra-fast laser pulse is we heat the iron. The nickel oxide and cobalt oxide are insulators. Heat propagates down rapidly through the stack. The cobalt oxide has a low Néel temperature, so we can switch off its antiferromagnetism suddenly, and then that causes the nickel moments to ping back towards the normal direction. And that all happens on a time scale of a few hundred femtoseconds. Okay, and yeah, I should have told you that the other nice thing about this stack is we can actually set the film in a single domain state in terms of its antiferromagnetic domains. That's important. Okay, so we can do our pump probe experiment. This is the measurement geometry. That's the optical plane of incidence. The circle is the sample with its crystallographic axes defined, so the moments point either along 110 or 1 bar 10. And when we excite it suddenly with the laser pulse, what do we see? Well, if we measure the transient reflectance, we see something that's very characteristic of a metal, a sudden rise and then a slow relaxation. So that's just the iron layer on the top. If we look at the rotation of the reflected probe beam, we can look on different time scales. If we look at the longer time scales first, if we polarize our probe between the two 110 axes along, say, 010, we see a rise of the order of 10 picoseconds and then a slow relaxation. What that is the thermal demagnetization of the antiferromagnet. So it's the magnetic order in the antiferromagnet being slowly quenched and then recovering. But at the same time, we can see oscillations. So if we look on very short time scales, we can see an oscillation with a frequency of 1/4 of a terahertz. So antiferromagnets are also interesting because they have resonances in the terahertz regime. And we can see a longer period oscillation here. That's at around 30 gigahertz. And so what we have is a coupled system, an antiferromagnet coupled to a ferromagnet, and we're seeing the collective modes of that system. One is similar to the resonant modes of the antiferromagnet. That is the short one, and the long one is typical of the ferromagnet. Okay, so why is this relevant? Well, it's because it's rather difficult to probe the excitations in a thin film antiferromagnet. There aren't many ways of doing this, and we suspect that when we grow an epitaxial film, the resonances will be strongly modified due to the strain. And indeed, in bulk, this resonance would be at 1 terahertz, and we can see that it's been modified by 1/4 of a terahertz in the thin film. As far as I know, this is the first time it's been detected directly in one of these time-resolved experiments. Okay, so I'm going to change gear, as I promised. How much time do I have? 5 minutes, okay. Not including the questions. Okay, so I'll go real quick then. So the attraction of van der Waals bonded materials is that are lots of different types, and what we know is we can stack them together easily. So in the case I'm going to talk about, we're going to stack a semiconductor with a magnetic van der Waals bonded material. And we can, because they're van der Waals bonded, we can have very clean interfaces, and hopefully we can combine some of the functionalities of the two types of material. So here we go. This is something that you may be familiar with. These are the transition metal dichalcogenides. If you make a monolayer of this material, maybe through mechanical exfoliation, then what you end up with is a semiconductor that shows spin valley coupling. So what this means is that at the K and the K prime points, you've got spin splitting, and it's an opposite splitting at those 2 points in reciprocal space. Furthermore, if you look at the optical selection rules, if you use circularly polarized light and tune to the band edge, it means that you can excite 100% spin polarized electrons to the conduction band of the TMDC. Okay, so the other ingredient that we need is a magnetic van der Waals bonded material. The chromium trihalides are among the first to be discovered. I'm going to talk about chromium triiodide. It turns out that it's ferromagnetic, even for a monolayer. If you go up to, say, 10 monolayers, it'll be ferromagnetic again. So I'll just move on quickly. The magnetic moment lies out of the plane. And because we're doing this by mechanical exfoliation, the flakes are very high quality, but they're very small. And that means an optical technique is a very convenient way of probing them. So the way we do it is we look at them in a wide field Kerr microscope and then excite with a laser. Our sample here is a flake of chromium triiodide with a monolayer of tungsten diselenide overlapping it, but not completely. So this just shows, we take a conventional hysteresis loop, we show that the tungsten diselenide doesn't affect the magnetic properties. But what we really want to do is then excite it with circularly polarized light. And if we do that, as we excite with bunches of pulses of opposite helicity, we see changes in the magnetic domain structure. And I'll cut to the chase because I'm short of time. If you look at a region well away from the edges of the flake, what you can see is when you excite with left and right circularly polarized light in sequence, the magnetic moment of the chromium triiodide flips from up to down to up and backwards and forwards. And in fact, you can do this at the single shot level. It's not so reliable. And cutting to the chase again, what's happening is when we excite optically, we do two things. We thermally demagnetize the ferromagnetic layer. We excite spin-polarized electrons in the tungsten diselenide layer. And then because of the band alignment, there's a transfer of spin-polarized charge from the TMDC to the magnetic layer. And then that determines the direction in which the magnetic moment cools again. Hence, we have deterministic optical control of the magnetization. And I don't have time for this, I'm sure. Okay, so of course, what we really want to do is to understand how the magnetization changes in time. So we built a new instrument to do that. It's basically a beam scanning microscope where we have a probe beam which we scan with a pair of galvo mirrors, but it's time resolved because we also introduce a pump beam here which isn't scanned. It's a larger diameter spot, so we excite with that, and then we take a scanning image of the response. And I have a final, that's the instrument in the lab, and the final slide is just some nice data from some CGT flakes. So these are a couple of flakes of different thickness, and what it shows is that the time-dependent response of the magnetization when these flakes are pumped optically, it depends very strongly upon the thickness of the flake. And really that's just a thermal effect. It's because the thermal transport in the CGT is strongly anisotropic, and it takes quite a long time for the heat to get out of the magnetic flake into the substrate. So now I'm sure I am out of time, so I'll conclude. So I've shown you that magnetic order and antiferromagnets can be a lot more accessible than we might previously have thought. We are developing the means to manipulate magnetic order and antiferromagnets, both by current injection and optically. I've talked about the van der Waals bonded few layer materials, which can give us new functionality, and I've shown you that all optical switching has been demonstrated in bilayers of ferromagnet and transition metal dichalcogenide. And the idea here, one of demagnetization followed by spin transfer, is something that we can transfer to other classes of materials. And in fact, that's something that we're currently working on. We want to do this in metallic materials that can be deposited by sputtering instead, because that's something that we could, in principle, put on the surface of a magnetic hard disk drive. And I'll end there.
Terrific. Thank you so much, Rob. So we do have a few minutes for some questions, if there are any. I'll let Joe go first.
Thank you for the talk, Rob. You talk at the end about this kind of constrained heat transport into the substrate. What if you had 2D systems on top of other magnetic systems? Would you see constraints in the spin transport depending on the thickness of these flakes or not?
Well, that depends. So
on what?
Well, it depends firstly upon the spin transparency of the interfaces, and then it depends upon the spin diffusion length within the flakes themselves. The materials that we're most interested in looking at, you would hope that the spin diffusion length's a lot longer than the thickness of the flake.
Do you have a concept of like instead of a heat capacity, can you have a spin capacity of a material?
I don't know.
Me neither.
Yeah.
Thanks, Rob.
I was going to just ask a more general question about sort of moving forwards towards actual applications and sort of predictions of where we're going forwards and what are realistic timescales and where the applications of these materials might be?
So it's easier to start with what I talked about last. So in terms of optical control of magnetic material for data storage, the recording industry has a roadmap for that. And the current method, well, which is now in product, which is heat-assisted magnetic recording, it goes on for another 5-10 years, and then we need something else. And the spin transfer mechanism is the something else. And there are different ways of doing it, potentially. I happen to like the spin current method, but other people talk about chiral phonons coming from the substrate. Circular dichroism might be used. I prefer the one I talked about.
Okay, maybe I can have one.
Yeah.
So, you know, these samples, they're very thin layers or very small flakes, and, you know, it's tiny amounts of material. Interfaces are very important. Sort of harking back to the session this morning on characterization, you know, what ways are there to kind of characterize the structure of the material and really know what the sample is that you're looking at?
So that's not usually my job. I make the optical measurements. So obviously you need some atomic level probe to do that. I mean, I sold it by saying that you could make very perfect interfaces because the flakes themselves are very perfect. But the truth is that when you stack them, you get little bubbles of gas, or you get the odd impurity trapped underneath, you get crinkles. So it's not perfect. A better way of doing it is to stack them in vacuum. And actually, Roman Gorbachev in Manchester's got a vacuum stacking station, and that looks very impressive. So, or you could actually deposit the materials, but that's being worked on. I'm not an expert in that.
Okay. Right, let's thank Rob one more time then. Hartwell, Thomas Hartwell, and he's from the School of Chemical and Process Engineering here in Leeds. He's completing his PhD at the moment, having also done his undergraduate studies here at Leeds in theoretical and mathematical physics. And this is something of a, not just theory, I think, but something of a change of gear in topic. His PhD research is to do with obtaining a deeper understanding of the underlying quantum mechanical processes occurring in quantum photonic technologies. So he's going to be the final speaker and complete the session today, talking about photon emission without quantum jumps. So please, Thomas.
Brilliant, thank you. Yes, so today's talk, or my talk for this, is going to be a little bit more theory-based than the other talks, but we do have some interesting experimental realizations towards the end. So a lot of the motivation for this work stems from photon emission is inherently a problem that's been an issue in quantum physics for the last 100 years, since the birth of quantum physics. We normally have all these nice master equations where we make all these assumptions and approximations to try and model how light works. The issue with this is it's not exact. So if you're trying to do anything that's more complicated than realistically 2 atoms, this becomes very, very tricky to do very quickly. I've got a little schematic here showing of, like, you can sometimes lose these like higher order perturbations, because this would be the rotating wave approximation. We also do what's called Markovian approximations, where you imagine the state has no bearing on its previous experiences, which is very unphysical and doesn't allow us to really comprehend what the light's doing. The big issue with these master equations, above anything, is that you end up losing a lot of the information about the field. So the way we calculate them is you trace out the field. You don't know what the light's doing once it leaves the emitter. You can only get a density matrix and a master equation for the actual atom and emitter. So we were thinking about this and we was like, okay, we need to come up with a new methodology to allow this treatment of the atom and the field so we can put it all together and hopefully do some quantum sensing. What we come up with is this idea of a local photon framework. So this stemmed from the idea that experimentally we know photons can interfere before they reach a detector. that implies there's some kind of process and like a gradual process of the emitter producing light into the field, and this gradual process is allowing some interference effects to occur. We like this idea of modelling it like a water bucket. This sounds a bit silly, but it's a really nice analogy for it. So if you put a hole in the bottom of a water bucket, we know lots of water is going to come out instantaneously, but it's not going to empty as a spontaneous jump, which is our quantum jump we normally think about. Instead, it's this gradual process of the water going into the field. And over time, there's going to be less and less water coming out until the bucket is completely empty. That's what we're proposing light actually does when it leaves an atom. It's not a single photon being emitted, it's a gradual decay until all of the probability of the photon has left the field. So in theory, it should be possible using some kind of local Hamiltonian, it should be possible to solve the Schrödinger equation directly and get some exact solutions. So this is where we come on to our Schrödinger cat analogy here, which follows on from the water bucket. So we get our interaction Hamiltonian, as you can see down here. We just have G here is some coupling constant that allows our emitter and field to interact, and so we never have to lose the field states. We have the normal bosonic annihilation operator in the A dagger, and the normal sigma minus is just our atomic lowering operator. This is all normalized and Hermitian, so this all works for a wave vector. So what we say is if our cat is, our normal Schrödinger's cat, I should say, just if anyone not familiar, is the thought experiment of a cat in a box with some kind of radioactive vial. If you don't open the box, you don't know if the cat's alive or dead. When you open the box, you find out. We're saying the same with light. The cat starts off alive, that's our atoms excited, the energy's in the atom. Over time, what will happen is the cat can become unwell, and we get into a superposition between our excited and ground state of our atom, and then what will happen over enough time is the cat will sadly pass away, and the photon will be emitted, but depending on the measurement problem, we could also have the cat becoming well again. We could give him his medicine, is the analogy we gave. We had a lot of fun with this. For anyone wondering, the cats are hand-drawn, and I would take commissions if anyone wants a scientific drawing done. But yes, no. So this is the idea we're working with, this idea of it's a gradual process going into a field, and there's this superposition of states until a measurement is taken. So what do we actually see from this, and how is this actually interesting? So when we solve these dynamics, what we see straight away is we get these lovely wave packets come out. So if we look at the probability of finding the photon somewhere in the field, we get the exact same as what you'd expect from this water bucket, where the most of the probability of finding a photon is going to be at the distance away from the emitter multiplied by the time since it's been emitted. What we've plotted on this top graph here is just 3 different times, showing that it propagates away completely in agreement with causality. It doesn't propagate faster than the speed of light. It propagates away like such. And the sort of harsh point where, the 3 harsh points, that's where the light, the maximum part of the probability density would be. Since the probability density has 2 variables, also has a variable on time, we can also look at that with a fixed position. The analogy I like to think of with this, again, is if you used to stand in the middle of the room and there was water to come from one edge, the gap before the sudden jump in probability is when the water hasn't hit you yet. You're initially going to be hit by the most water. That's your highest likelihood of finding a photon. And then that's going to gradually go down because there's less water in the bucket rushing at you. You're going to get less wet. As you can tell, we really do use this water bucket analogy a lot for all of this. We also calculated our decay rate from all of this. This fell out of the maths really nicely. It ends up being just the coupling between the atom and the field divided by the speed of light. This was a really nice little finding because it's something that we're playing with a lot with lots of different experimental applications now, because the decay rate is not something that normally is nice and simple to calculate. It's normally an experimentally found variable. We then was like, okay, this is really cool. Let's do some Fourier analysis on it because that's what physicists do. And we managed to move into momentum space. And what we found was we get a Lorentzian shape out of this. We get the exact dynamics you'd expect, shape-wise you'd expect from an experimental perspective, where we can just say an atom in free space is emitting light. We get curves which are dependent on the width of them are the half of the decay rate squared. Again, we have 3 different decay rates here. Unfortunately, these are a little bit zoomed out because I didn't have access to a higher performance computer to make them a bit more zoomed in, but the premise still stands. So this was a really nice finding as well. So from all this is really interesting theoretical work, but we then had the issue of, okay, how can we make this a bit more useful? And we was like, well, okay, let's introduce a mirror. So when you have this two-level system in front of a mirror, this is again a system that is very hard to model without any kind of approximations, unless you use this new method of having this local excitation and coupling. So what we say is, again, the atom just couples to the field, not to a mode. So normally you think of these in terms of wave modes in a waveguide. We don't want to do that. It's going to couple with this factor G, and our semi-transparent mirror or surface is just going to be traditional with a reflection and transmission rate that it can hit. What we see from this is as the light goes towards it, we get, if the light doesn't have enough time to interfere with itself, we just get our normal free space dynamics. This is what figure A here is showing, that this is pretty much identical to if the mirror is not there. This is what we would hope for. If the amount of time for the light to travel to the mirror and come back is on the same order as the rate of decay of the atom or emitter, you can get either figure B or C here, which are really interesting, where we're able to produce some enhancement of emission so the atom decays quicker, or we're able to slow down the emission. So there's some really interesting work being done, I believe it's in Oxford by Axel Kuhn, who's looking at shaping wave packets. He's managed to make like an Eiffel Tower out of light using these kind of ideas where you can actually shape the light that's coming out. It's fascinating stuff, and we're now able to do it completely exactly with no need to assume anything. The last figure here is also really interesting because this is when our time period gets a little bit longer. What we can see is the atoms, you're getting these small perturbations, and this is the atom re-exciting itself. This is something that's quite hard to see from the master equations because it just gets too complicated. So what we're seeing is the atoms reabsorbing the light, and we're getting this gradual decay, sort of like the water's going back into the bucket and flowing back out again, which is really nice. So this is all, again, that was the theory side of this. Experimentally, there's a group that started in Leeds, I think it's about 3 years ago now, called NIX, who are working on a non-invasive quantum sensor. And the idea of the sensor is it's a diabetes sensor. They're looking to monitor the glucose within blood, using all of these ideas of this local coupling and local photon approach. And what they have seen, this was a November 2025 that's come out, that they have managed to get a 99.3 clinical acceptability rate and a 95.7% clinical accuracy for the amount of glucose in a patient's arm, or in a patient's body, I should say, compared to that of an exact replica. And for normal photonic methods, this has never been done before, especially non-invasively. There are a handful of other sensors that work on a semi-invasive method, but completely non-invasively, this is a nice breakthrough with that. And that pretty much summarizes the application, I suppose. So this is, as I say, we're able to have some kind of light that couples to it and has a actual real-world medical implication directly. And using these methods, we're able to describe the sensor now and hopefully model it and improve the quality of it. So obviously I've gone through this all quite quickly, but just to conclude, we have suggested a completely new framework to predict the fluorescent profiles of optical systems with light and matter interactions. We are now able to model light and matter interactions, including mirrors, which again is something that's been done for well, not for hundreds of years, but it's been done for a long, long time, and it's something that is nice that is now able to do exactly. And finally, we have various possible applications in quantum sensing. For us, non-invasive diabetes sensing is where we're looking, but there's lots of other fields this could be applied to, and we're looking into that in collaboration with a few other universities. So thank you for your attention, and a massive thank you to my supervisors, Jin and Alma.
Brilliant, thanks, Thomas. So we do have a couple of minutes for some questions. I think Rick was ever so slightly faster.
Are there any implications for if you've got sort of a group of emitters side by side?
Yes, so we're currently looking into, so the current bit of work I'm doing is 2 emitters and look in a waveguide and looking at like a one-dimensional solution to that. We're really interested in the sheet of emitters because that's obviously going to be way more applicable to larger scale systems. Our prediction is that the way, if you have them confined to a pretty narrow, so there's only 1 or 2 atomic thickness, there should be almost complete destructive interference in like both directions of the plane. So we're hoping we can direct the light, hopefully quite controlled in a set direction to an error. That's the prediction. We're currently doing that. We haven't finished it yet. That is the idea with that, yeah. Thank you.
Thanks. There's another one over here.
maybe related to that question, everything you talked about is single photon.
Yep.
What happens if you have multiple photons or maybe two entangled photons? Can you cope with that in a local picture?
Yes, so two atoms, as I say, is what we're, two atoms, two photons, that's what we're currently looking at, and that's where we get these really interesting reabsorption effects where with what we've realized you can almost treat the second atom as a mirror. And sort of the absorption and reflection, or the reflection and transmission rates are very similar to the absorption and non-absorption rates. And that's a really interesting way that we can now have these sort of macroscopic systems and scale them down or vice versa, which is really interesting. Entangled, we think there's an application for an entangling scheme with this. That's something that we had a very little look at and realized that was going to be more complicated than we had time to work on, and that is potentially another paper down the line, but that's something that there's an application there we just haven't really dug our teeth into yet. Thank you.
Okay, let's thank Thomas once more.
Thank you.
So Claire tells me there's a very short 5-minute sort of comfort break now between the sessions, so we're going to restart at 3 o'clock. Okay.
Another couple of minutes.
I'll wave around after you've had 20 minutes, and I'll wave around when there's 5 minutes left. How are we doing?
You're very keen.
Sorry?
You're very keen. Okay, let's go, guys.
Go for it.
Well, I think we'll start again. So welcome to the last session this afternoon before the posters. So this is all about soft matter. It's a great pleasure to welcome Joao Cabral from Imperial College. Joao's a great stalwart of the polymer physics community and the soft matter community in the UK. He's done loads of great work on polymers and phase separation and droplets and all kinds of things. But today you're going to be telling us about design and function of asymmetric polymer networks. So away you go.
Amazing, thank you. Can you hear me well at the back? Fantastic, thank you. So I'm opening this soft matter session, so we are really sort of shifting gears now. And the title is maybe a little bit cryptic, but it's on polymers, so polymer networks. These are cross-linked polymeric networks that are macroscopic, so things that we can hold. And they are asymmetric, and asymmetric here means that they have a facet that will be different from what's happening in the bulk, and we'll try to harness that asymmetry for some kind of function. And that function might be motility, actuation, swimming, those kinds of things. So it's an area of active matter. And the work is won by one of my PhD students, Gifari Ridwan, who's funded by a UKRA, I guess, supported doctoral training network that is also part of an EU network, and then 2 EPSRC-funded past postdocs, and some collaborators from NIST. And it's work that we've done at Imperial over the past few years. And the context is that of sort of solidification of materials that start off being a monomer, so that's a short unit that then gets polymerized into some bits. And the one type of 3D printing that we're mostly familiar with might be this FDM, which is something where we take a filament, we melt it, and then we solidify it readily and make it adopt a shape. But just as popular, we have photopolymerization, where instead you have here a monomer bath, that's the monomer in the liquid state, and we use light selectively to solidify it locally, and then the outcomes, they have different quirks, but the outcomes are similar. You solidify something from a monomer. This is the one that I'm going to focus on today, and in detail, it's more or less what we see over here. We start off with a bath of monomer that's uncross-linked sort of material that is subjected to some kind of light exposure. Often it's UVA. And here the detail, the way we're going to try to create the asymmetry is by harnessing the fact that this is a directional process. So typically, we solidify a chunk of a material, but under certain conditions, we can make this propagate like a front, so it becomes like a traveling wave. And this traveling wave can be exceptionally sharp, and it gives us all sorts of control, because laterally you can control that by the light exposure or a photomask, so you have XY control. But along the vertical direction, you really should have no entitlement to being able to do any kind of control. But if you make this front sufficiently sharp, and you can allow this wave to travel on demand, then you can also exert control over the remaining dimensions. So you get some kind of 3-dimensionality of the pattern. Now, we, as Daniel mentioned, we are kind of coming in from a polymer physics perspective, and so these types of models kind of makes us sort of take another breath. So the detailed modeling of a process like this is not complex, but it's complicated in the sense that there are many steps. So you take a a photoinitiator that, with the action of light, creates a radical. That radical meets a monomer, and then it starts the polymerization process, first with a few units, then with more units, and then there are all sorts of reactions that you can write them down, but they're complicated without being sort of complex. But solving these it requires this system of many partial differential equations and a number of parameters. Many of them are really not meaningfully measured. So in this one example I picked, we have 43 parameters for this model, and many of them cannot be experimentally measured. So we kind of thought, well, can we do this in a different way? And being sort of now, I'm in a chemical engineering department, so being more of an engineer, we kind of thought, well, what are the observables? And they are primarily two. You can measure how tall the stuff is, so the pattern dimension, and you can also readily measure the light attenuation. And we kind of asked, in some simple systems, what's the simplest possible equation that I could possibly write? And that turns out to be, rather simple. So you could say, I can write an equation of motion for this, maybe let's call it a mean field or an order parameter that accounts for this conversion between a liquid into a solid, this liquid monomer to polymer conversion. And I say that this rate of change is proportional to some kind of light intensity, so how intense the light is, some kind of, or how many sites are left, so a 1 minus 5, 5 being our order parameter, and some kind of rate constant. And we can call this the equation of motion for this process. And then the second equation, it might look a little unusual, but it's just the Beer-Lambert law in a differential form that just tells us that the light is attenuated in the depth, so that's in the Z coordinate, and it's proportional to these attenuation coefficients, and those will change whether the material is still unpolymerized versus polymerized. And you need some kind of closure, and that is to say that at some point you reach some percolation condition, and that has become a solid. It's a very weak network. Think of it as gelatin just about to go into the solid state. It's still wobbly, and it's very weak, but there's a perfectly legitimate critical threshold. And then eventually you can polymerize this ad nauseum, which is what you do, for example, in photopolymerization, where you do what's called a post-cure. You say, once the shape is defined, let me just expose this, flood expose it until the solid has the mechanical properties that I need. So this is the cartoon. You say, well, I start with something that is virgin, and then upon the exposure of light, layer by layer, eventually I fully polymerize it. And so I start with 0 of my order parameter, and I end up with 1. And in the middle, if I played my cards right, I should get some kind of waveform, some kind of sigmoidal that might propagate. This is kind of the realization of that ultra simple model that says that on the left, light is exposed from top to bottom. The front propagates. This is our conversion. This vertical red line is this critical threshold. That's this kind of incipient gelation or percolation condition. And here is the position of this front with respect to time. I kind of want to emphasize these are really waves in the sense that they have a lot of properties that you would expect from a wave. You can define the profile of the wave. They can interfere in a very interesting way. You can form multiple networks through this interference process and so forth. So this is kind of a summary of what I mentioned. The optical properties evolve over time, and with the position, this conversion evolves, the rate of the polymerization evolves, and I can track its position over time, and I can model this, because that's the advantage of, I guess, doing modeling. You can dream up things, but I'm mostly an experimentalist, so we wanted to check whether this worked in practice. So we take here a thiol-ene system. That's a simple network polymer-forming material that we use in a number of applications, for example, even as adhesives. And this is the experimental data. This is spectroscopic sort of cross-sectional data. And this is this kind of our prediction, if you wish. The line is the theoretical prediction in one of the simplest cases. And what you can see more interestingly is well that the wavefront is shape invariant. So this is really like a wave that propagates with a speed, or in fact an acceleration and a speed that we can control separately, and also with a width that also can be written down and based on these kind of model parameters. I mean, I have many friends who are chemists. Of course, this really irritates a chemist, because this is kind of getting away with murder, right? We've neglected all of the chemical details, and we've assumed that this is just some kind of mean fields, almost chemical agnostic system. And to some extent, we do get away with murder, but not always. I'll show you in a second. But you know, on this, the model predictions are quite neat. For example, here it tells you that if I look at this mu, the optical attenuation coefficient, it tells me that if I tweak mu, then I can change the rate of propagation of this wave. And this is kind of an example of a realization of this. These are the scaling laws that we predict with this super simple model, and I've just doped these with carbon nanotubes or silica, just trace amounts of fillers, just to play around with the optical properties, and the predictions kind of nail it on its head. For example, if I wanted to adjust instead the rate constant, I could maybe vary that with temperature. These are Arrhenius simple reactions, and indeed that works because that slides this propagation sort of rate law horizontally, just like this simple model would expect it to do. Now, I wanted to be kind of honest with you that this doesn't apply generally, evidently, because at some point, you know, you get caught out. So, for example, a lot of these reactions can be exothermic. A polymerization reaction is often exothermic, and so temperature will mess you up because that will create some kind of feedback that will change a lot of our predictions. And in fact, another part of the work that we do is to harness that, I guess, exothermic nature of these. And if you design the reaction to be sufficiently exothermic, it will become autocatalytic. So you don't even need light. Once you start the process, the reaction will proceed happily until it's run out of material. So there are so many aspects to this that I've started working with this problem many years ago, and I remain fascinated by this. But as I say, these are not complicated, these are not complex problems, they're just complicated. If I need to introduce some feedback of the, say, reaction constant, or maybe heat, some diffusivity, I can do that. That's not an issue. But the bottom line here is that, well, we can account for this, and actually, by and large, it doesn't really matter. So for the majority of systems that we've looked at, this kind of minimal model for the planar polymerization works. And so that's kind of what I wanted to tell you in the introduction, is that you have a process where you take a liquid that turns into a solid. It does that with light. It's what we use in photolithography or 3D printing through photopolymerization. And it can naturally predict the conversion with some minimal number of parameters, but also allows you to design the actual details of that interface and the propagation of these planar waves. And so we've used this to make, say, microfluidic devices, because you can make three-dimensional structures with these. You can even make a sort of aspherical optical elements, for example, if you design this kind of grayscale around this let's say, a photomask to create sort of lenses, for example, except that their surface quality is not very good, because they will simply take over what, say, the photomask has given it, unless you use some other tricks. Except that this is not always true either, right? So I've given you the kind of the talk of the well-behaved, sort of the royal path. This is planar, it's well-behaved, etc. Except that it isn't. So very quickly we realized that occasionally you see some kind of unpleasant roughness on the surface. And then you look into detail, and this is where I think, being fascinated by materials, we need to kind of keep our eyes open. We realize that the noise on the surface, the roughness, isn't just roughness. So you see that these, I mean, they have a characteristic length scale. So if you do some kind of image analysis or some kind of Voronoi tessellation analysis, you can count the number of neighbors, the coordination, therefore, of each of these cells, and you can try to, figure out what is happening there. If you look at the interfaces at the edges, this is now a top view over an otherwise planar surface, you realize that under some conditions, you have these dendrites that seem to kind of break symmetry at the edges and kind of emanate in a very geometric way. So the kind of the short of the story so far is that in many cases, polymerization is perfectly planar, and that's why we use it for materials manufacturing. But there are these surprises, these instabilities. This is a wrinkling instability specifically. So it's one where we have a kind of a wavelength that depends on some kind of material properties. I'll tell you that in a bit more detail. So we have a wavelength and an amplitude and some kind of mechanical condition for the emergence of this instability. The instability, as I mentioned, is a wrinkling instability, so it's related to our own wrinkles or the wrinkles on the surface of fruit, for example. If you go on holidays and leave an apple, as the volume of the apple shrinks, the skin undulates. And so it depends on the mechanical properties of the film, if you wish, of the substrate, so effectively the modulus, or in this case, the plane strain modulus. It depends on the thickness of that skin. In many ways, it is very much like our own wrinkles or fingerprints on our skin, because the epidermis is thin and stiff, and the dermis underneath is soft and squishy. And the mismatch between both, because they are bonded together, means that once you apply an external constraint, they need to negotiate somehow. One is able to accommodate the deformation, the other one is not, and the outcome is an undulation. So that's what happens here. It's an emergence of an undulation, and is one that in many cases we can control, as you can see, very precisely. And here, well, this is happening live, right, as this wave is propagating, so we kind of needed to work a little bit harder. You can absolutely model this. This is experiment, this is the theoretical measurement, the theoretical simulation, and the experiment, they match quite nicely. But what we realize is that I mentioned to you that the edges kind of break the symmetry of this problem, and we're always thinking in engineering to how to make stuff work for us, right? And so we can absolutely suppress these, but we thought, can we make something useful out of those? And the answer is also yes, because if you impose the lateral dimensions to be commensurate with the length scale of this instability, which you can design in the way that I showed you, you can excite some kind of minimal shapes. For example, here I've made this into a triangle, and this creates a pyramid with very well-defined, out of two-dimensional mask, you're generating a three-dimensional object, and that's not even going to the next layer, so to speak. And you can even generate chiral materials by breaking the symmetry of this process. So what's happening here from a polymer, I guess, science point of view? It happens that you have a network, and that network has a gradient, and it's the polymerized material is in contact with the unpolymerized material, but they are effectively the same thing. One is already polymerized, a step further, the other one is not yet polymerized. They actually really like each other, and the liquid material can release some of the conformational frustrations that the network has by invading it, by diffusing back into its cocoon, if you wish. And as it does that in the appropriate timescales, it will swell that material and will generate this instability. So that's the source of the mechanical instability. And as I mentioned to you, we can write a detailed model for this, and the outcome is that now we can design precisely smooth optical properties, for example, for lenses that have otherwise need to be made mechanically polished, etc., in a rather complicated way. So that was, I guess, one initial surprise, which is an instability that we can trigger on or off. And then initially we were disappointed by this, and then later I think you can harness that to some good effect. The other instability that I think is fun, and that this is the work of my PhD student that has just been published this last week, is on some kind of curvature or warping. It's again, for those of us who've used a 3D printer, we've all seen this. It's when you've made the material and everything looked good initially, but over time, this thing starts deforming, in acquiring some kind of curvature, and often debonds or delaminates the substrate. Those of us who use lithography, we've often seen this. And this is an example of what that is. This is that frontal process, and if you make a material that is sufficiently thick, the energy required to bend it is so high that it acquiesces and remains planar. But otherwise, I mean, this is a gradient material. Of course, there are asymmetric stresses along that kind of normal direction to the surface. And so if the material is sufficiently thin, it will curl up like, I guess, butter, if you wish. And so this is that kappa is the curvature, is effectively the inverse of the radius of the kind of an imagined circle around this material. And, we can design that curvature to some extent. and this is, again, this is generally an undesirable kind of instability related to these unrelaxed stresses. But if I look at this video, this kind of made us scratch our heads for a little while. It's a material that is warping, so we've designed it as a 5-leaf sort of flower, if you wish, but then it kind of changes its mind, and it's going to curl back and, in fact, decides on a new curvature. And in this case, this is so 5 leaves, and it curves in one direction, then it curves in the other direction. But we kind of wondered, why did it change its mind? You know, why, if it knew that it was going to warp, why didn't it go there in the first place? That was the first thing. The other one is, of course, we're always thinking, how can we make use of this? Can we, for example, induce locomotion? Can we use this for example, gripping objects and carrying them across? And can we control this? Can the flower open again? And the answer is yes to all of those questions. But first, of course, we needed to find out what is indeed kind of happening. And so here's a kind of how we can write something for, I think I'm missing something there, but how we can write something for this, see if I can click in the right place. No. How we can write something for okay, now something is there. So so in a nutshell, we have a material that has a dimension, a given thickness, right? So we have 2 interfaces now. We have a base, so to speak, or a front, and they are, as I mentioned to you, asymmetric because this is a directional process. Now, what we expect is that these are gentle network materials, and so the susceptibility of these to diffusion of liquids, but also gases, is different. It's asymmetric, and hence the title of my talk. Here we're trying to see how we can take advantage of the often unpleasant asymmetry that these photopolymerizable materials have to harness some kind of function. And in this case, what we're doing just that. We are realizing that one end of the material is more highly cross-linked than the other, and so the uptake of a gas will have different kinetics, but also if you wish, the absorption capacity of each facet is also going to be different. And so our sort of research hypothesis was that one is a thermodynamic property, the other one is a kinetic property, but they are both asymmetric on either side. And if we could design both sort of predictively, then we could start maybe shape-shifting the materials like this. And so that's kind of what my student has worked on. And this is a realization of, Z is the coordinate, here is the concentration. In this case, we are using a volatile, because we want this to be relatively fast, we're using a volatile solvent like acetone to induce this. The model is, again, very simple. I am, unlike Daniel, I'm primarily an experimentalist. So this is, again, a coarse-grained model where we try to write an equation for, this is just a Fickian description of a process. So it's the simplest that we could come up with, not even including any of the details of the polymer molecular structure, which I'll come to in a bit. So at the moment, I'm just thinking of this as a lump of plastic that is wonky, has one shoulder that is higher than the other shoulder, so it takes up more or less, or faster or slower, solvent or liquid. And so the first one is assuming this material is completely homogeneous. I can write an equation for the modulus that depends on the concentration of this. Sometimes the engineers call that the penetrant, is this new species. I can calculate the strain, and then this Z is the neutral axis. That's what decides whether it's going to curve one way or the other way. And what we see here is that we can design effectively a dance of the neutral axis that fluctuates to be sort of above the median of the material, and so it will curve upwards or below, and then it will change its mind. And this process can be done repeatedly by this exposure. Okay, so that was, I guess, one way, but in this case I have, with the same process, another instability. This is now a snapping instability, which is where this material is functioning like a spring. We've designed it in a way, let me play this again, because this is now jumping quite high within about 10 milliseconds. So it's going to curl initially like a spring, and then it will jump. I mean, if anyone has ideas about how to do that, we want this guy to be able to jump a number of times. And so the way it's jumping now is that it now needs to curve backwards, store energy one more time, and then it will snap and jump one additional time. And it can go on for a long time doing this. But we haven't found a way to guarantee that it's going to, when it falls, that it falls always in the same way, a bit like when you drop something on the floor. So this is another way of inducing function through locomotion, simply using the asymmetry of the material. We have not done any complex design. I'm kind of running out of time now, but what we're working on now is that this is happening in the gaseous environment. This also happens in a liquid environment, where we change the neutral axis so that it generates a swimmer where the material is below water for some of the period to store energy, and then it will propel. And the neutral axis changes so that it's then above the level of that liquid. And so it can repeat this process a number of times with absorption and desorption cycle. In this case, we've created a switch, and this switch can also go on a number of times as we change the conditions externally. And you can see this is just mounted on a 3D printed frame. This is just the switch itself, and these are these asymmetric networks that we've placed on a frame so that we could probe this. We call this is called a bistable switch. It's a very common design in this field of active matter, and this is, I think, the simplest realization of the bistable switch with a single step of light exposure. These materials are dirt cheap. I think you could see that I've been more or less omitting the chemical details because we've done these with, for example, polyethylene glycols, for example, PEGDA. That's the flavor of polyethylene glycol that is photopolymerizable. We've used thiolenes, acrylates, diallyls, triallyls, etc. This is a very general design framework. So final slide here is one, okay, well, I've mentioned to you one step, but sure, we can do 2 steps. It's not the full sort of 3D printing sort of effort, but with 2 steps, it's already pretty amazing what you can do, because if you believed my hypothesis, which is that I can design curvature with a single exposure, then I might want to design curvature differently. So in this case, I have something that has a low propensity to curve, so it's effectively a more cross-linked material here, and here I have effectively a hinge, and I can decide, because I know how to relate the exposure to curvature, I can design how much this hinge should bend, and if so, I can ask the question, what's needed for me to fold, for example, at 90 degrees? And if you can fold at 90 degrees, you can keep going, right? You design that. You can design an Amazon box, so to speak, at whatever scale. In this case, it's a millimeter scale. This is not completely, everything needs to be designed holistically like a system, but as I told you, the design, once you have a simple framework, and this is why I was so keen on not using a 43 model, sort of theoretical model, but rather a 2 model theoretical framework, because that allows you to now design. Here it becomes trivial to design, for example, a box that closes on demand at specific timescales within a couple of minutes, opens back again, releases whatever cargo we have, and so forth. And as I think, in terms of dimensions and moduli, the devil is in the detail, but this, as a design platform, this is really very democratic and accessible. So to finalize this last part was the work of Ghifari on the actuators and the locomotion. The previous work on the theory of the sort of non-isothermal processes and optically complex systems was from Matt Hennessy. The experimental work on the monomer design, Alessandra Vitale, and these are our other collaborators from a longer time. And as a graphical conclusion, we call this photo-frontal polymerization. So it's frontal, the F, and then photopolymerization, because there's also this other flavor, which is autocatalytic, doesn't even need the light. And I hope that I've persuaded you that you can make this process in 1 dimension very simply, and that you can write very simple models that account for a lot of the chemical behavior that we see without really worrying about the details. That under some conditions you can harness these instabilities to create these in 3 dimensions, even though this is a single shot. You shouldn't be entitled to expect any 3-dimensionality since you're just patterning in a plane. And that if you go beyond that, if you design this, if you understand fully the asymmetry of these, you can get them to start working for you. Gripping, swimming, picking stuff up, opening and closing. And the applications, I think, are many in not only in biomedical materials, but also in structural mechanics, in architecture at large scale. Some of these have been used to sort of open and close, for example, with exposure to light or exposure to environments. And there's a lot of interest in active matter at a smaller scale. So we're now working to make this as small as you can. Right now, we work at the scale of a few hundreds of microns to many millimeters or centimeters. We're trying to make this a lot smaller so that we can get it into the body. Thank you.
Excellent fun. So, do we have any questions? One there.
Chital.
You have to wait until the microphone gets to you.
Talk. Thank you for that. Very simple question on your dynamic materials. I guess they're reversible. How many cycles before you get some degradation? So how long do you think they'll last?
So this is an excellent question about the durability and the cyclability is like what we think in terms of battery materials or something like this. How many cycles can we get? In this case, these materials are network materials. Some of these are even self-healing materials because we cross-link them very lightly, in fact. And so they restore themselves quite readily, in fact. So the cyclability for us has not been so much of an issue. It's more how do we get and I've glossed over some of these details. How do we get the nudge to be as simple as possible? Because they will respond repeatedly, eventually, over many cycles, there are some cracks that form and some wear of the material. But primarily, for example, for us to get locomotion over long distances is how do we precisely adjust the dynamics of for example, that neutral axis that says curve upwards, curve downwards, in a way that we can, almost like you train a swimmer, you need to synchronize the swim such that you get the fuel in the right moment. It curves with the correct time scale that it will acquire a new fuel, and then it will continue moving forward. And we want the materials to work for us, right? We don't want to work for the material so that this only works in a very sort of narrow Goldilocks region. So that has been our challenge. Not so much the durability, but the synchronization of the acquisition of fuel and the function, if you wish. That's a good
Thank you. Anybody else? One from Edmund.
Can you talk about, have you sort of functionalized some of these surfaces by then coating them, or what can you do to actually sort of make them from the structure and folding you've shown to actually include other particles within that material?
It's a super good question about the incorporation of fillers or active materials whether within the bulk or on the surface. Within the bulk, for example, this is a kind of a classic sort of dispersion or even dissolution, because I mentioned to you, you can form these double networks, or sometimes called IPNs, interpenetrating networks. And so if two organic materials, if they don't dislike each other thermodynamically, you can generate dual networks with dual functionality. Incorporating fillers is met always with the usual questions of the miscibility and the kinetic stabilization of filled materials, composites. Often, if you're not careful, they will aggregate like there's no tomorrow, and the benefits are over. But for example, we wanted to make these electrically conductive by introducing high aspect ratio materials that would not bundle together, and those are successful. So they are functionalizable. Right now, I mean, I guess over here, I didn't talk to you about end applications, although we have some in dental materials and in 3D printing for structural materials. Dental is an interesting one because they have, if you have a sort of a filling in a cavity, for example, you know, if you go to the doctor, we've all probably had, if you had a filling these days, you'd probably have one which is a photopolymer, just like this. It's biocompatible, and critically, you want that to stay there, stay quiet for a long time, right? But one of the things these guys do is that immediately it's a polymerization process, they shrink. And so often that's why the doctor or the nurse, whatever, they go in and they press it a little bit more and they try to remove all the gaps, the air, because otherwise, you know, you'll be back in the dentist's office within not very much time. But so it turns out that, in fact, a bit of an anecdote, I started working on this when I was in the US, and the floor below where I was working was the American Dental Association, where they actually know a lot about these kinds of photopolymer resists because they use it for totally different applications. And they were also preoccupied by this asymmetry for all the other reasons, because, you know, your mouth is full of stuff, and that also gets into these materials. And so those were the two areas that we've worked on so far, so dental materials and structural materials.
We had better move on, but thank you ever so much, Joao.
Thank you.
Okay, so our next speaker is our very own Arwen Tyler, and the title is somewhere. I've got it. Nope, that's the electronic and photonic materials. We'll find out the title in a minute. So Arwen is from the School of Food Science and Nutrition, expert on lipids and scattering, and how they interact. Lipids interact with polymers and biopolymers and all kinds of things. So I'll hand straight over to Arwen. There we go.
Great. Thank you so much, Daniel, and thank you for the invitation. So I hope to give you a bit of a flavour of what my group does. So we're interested in lipids, so lytropic liquid crystals. And what we try and do is develop engineering rules to kind of predict and tune the structures that these lipids form, as well as tune their dimensions. So we kind of analyse our structures using a lot of techniques such as X-ray and neutron scattering. We like to use nature as inspiration for the materials we develop. And then we take these rules we try to kind of develop and then create kind of rational design of formulations rather than empirical ones, which you might know cost a lot of money and time and effort, and tailor them for various applications, for example, such as in drug delivery. So, you know, imagine if we can form a vehicle that goes inside your cells and then encounters a stimulus, and then that can release an active at the correct place and the right time as well. So curved structures do exist in nature. We don't live in flatland. So over here, you know, it's areas of our cell and certain processes like membrane fusion have curvature, so curved structures formed, and require lipids that promote some kind of curvature. So you can think of lipids a bit like molecular Lego. So they come in a variety of shapes. They could be like cylindrical-like, they could be inverted cone-like. And kind of understanding the geometry of our building block, then hopefully we can try and understand what the final geometric structure we might form as well. So we find them in nature. You can see them here, for example, in an amoeba mitochondrium. Also, the colour set in butterflies and weevils is not due to pigments, but is due to these curved structures, which end up acting as photonic crystals, so we call this structural colour. So you can see here some jewellery that royalty got given. You can find that at the V&A Museum in London, and you see this kind of beautiful structural colour. And if you're not royalty, unfortunately, you have to 3D print your own cubic phase earrings. I'm wearing mine today. So there we go. So what kind of applications these might have? In bulk, these kind of lipid assemblies are very gel-like, viscous. So we can use them, for example, in topical applications. Or we can break them up into nanoparticle dispersions, and then you inject them and deliver them in our body. You might know that membrane proteins are very difficult to crystallize. By actually embedding them in these curved structures, they kind of mimic the native environment, and a lot of structures have been solved in this way. You know, and if we can make them big enough, they can end up acting as photonic crystals, as I showed you with the butterflies. So it's kind of typical structures that lipids might form. Obviously, we've got a kind of fluid bilayer, ubiquitous in nature. Our cells adopt it most of the time. However, if there's some desire for curvature, for example, our molecular Lego is more curvy, more cone-shaped like, then we can form these kind of more exotic, beautiful mesoporous bicontinuous cubic phases, where we've got a kind of lipid bilayer which is curved and is separated by two water channels. We can form kind of cylindrical micelles that pack in a hexagonal array with water flowing through their core. Or we can have order micellar phases where here kind of inverse micelles pack into a periodic lattice, in this case a cubic one. And actually by tuning the kind of symmetry and as well as the dimensions of the water channels in the case of these guys here, which are mesoporous, we can actually tune the release of any active we might encapsulate within them. So I'll give you some examples. This is some work we've been doing on kind of nanoparticle dispersions, which we make either microfluidically or with top-down approaches. So one thing we wanted to develop was a pH-responsive delivery vehicle. So pH gradients exist in our body. So for example, cancer cells tend to be a bit more acidic compared to healthy tissue, also various organs and organelles in our body as well. So we thought it'd be really neat if we can, design a little nanoparticle that forms this kind of discontinuous structure. So you've got these little kind of inverse kind of aqueous pockets, if you wish, and you can put an active within them, and then that active should have very little or no release out of them. But then by changing the pH, then the structure can rearrange to this more accessible mesoporous one and release an active through the pores. So this is what we tried to do. So we made some nanoparticles that formed this FD3M phase internally. And what we did is we doped our system with a tiny amount of an ionizable lipid that when it becomes charged by lowering the pH, it should tune kind of the interfacial curvature, and the hope was then it will switch to this less curved structure. And luckily for us, this is what it did. So you can see here some X-ray scattering data, so at kind of a physiological pH. We've got this FD3M nanoparticle. And then as the pH is lowered, we form these hexosomes. And importantly, again, this transition is reversible when we reverse the pH. And obviously, with SACS, we're looking kind of ensemble of averages, but we have some amazing facilities here in Leeds where we can do some kind of cryo-TEM and visualize individual nanoparticles. So you can see here at physiological pH, we've got these kind of FD3M micellosomes, and then we lower the pH and we form these hexosomes. And of course, we can use this data as well to also index the structures we form. But what was really cool for us was in the past, these kind of FD3M nanoparticles could not be visualized by other groups using electron microscopy, and they kind of look like amorphous blobs. So kind of we came up with some ways to be able to image them, which was really nice because we know actually from our X-ray data they do have a periodic internal structure. And depending on how our nanoparticle sat with respect to the electron beam, we could either visualize the larger micelles or the smaller micelles that make up this kind of structural motif of the FD3M unit cell. And what we calculated for our experimental data is in perfect agreement with what the theoretical structure should be as well, which was really exciting for us. Another thing we tried to do is try and understand how these nanoparticles interact either with real cells or artificial cells. So I'll give you an example of some kind of interactions of cubosome nanoparticles with artificial cells. So I think it's really, really nice how we can now use kind of material engineering approaches to design biological machines that have certain functionalities. So the kind of motivation behind this work was twofold. Firstly, well, real cells are very complicated, so if we can make a kind of model cell or artificial cell, our life is easier. So we use as giant unilamellar vesicles as kind of model cells. And we want to know how these nanoparticles interact with these model cells for a fundamental understanding during processes like drug delivery. But also in the artificial cell field, we said real cells are complicated, but can we mimic some of the functionalities that kind of real cells have, such as growth and division, but in a more simplistic way? So we take our kind of artificial cells and we throw these kind of cubic nanoparticles on them. And we were hoping that these can be one of the tools. A lot of people use other tools like temperature jumps or kind of osmotic shocks. But we were hoping these guys, which tend to be really fusogenic and have these curvy lipids inside packed into this nanoparticle, can potentially act as minimal triggers of various morphological and topological transformations. So this is kind of what happens. The first thing we see when we throw our nanoparticles onto our GUVs is we see the GUV swelling, so our GUVs grow, membrane surface area increases, and so on, and we characterize this using a variety of techniques. And then after we kind of get this swelling, we reach a stability limit. So these kind of cubosome nanoparticles have these curvy lipids that don't want to be constrained in the flat bilayer. So incorporation of these that fuse into the membrane of our GUV causes a significant amount of stored curvature elastic stress. And then this can be released by a variety of ways. So for example, formation of nanotubes, so external ones or internal ones here. We see events such as fusion and fission. So here we have two GUVs labeled in two different colors. We add our cubosomes, and over time you see this kind of two GUVs fuse and become a single GUV. We see a GUV giving birth to a baby GUV inside its belly. We also see examples of fusion. So here we have a kind of mother vesicle generating a smaller vesicle and popping it out. And if you can see, as our GUV kind of starts incorporating these cubosomes, it swells, and you can see from the area and the aspect ratio, they're very much not spherical. And as these kind of GUVs undergo these morphological and topological phase transitions, they eventually re-equilibrate and become nice and spherical again. There are also other things they can do. They can form these kind of intraluminal vesicles, so little subcompartments between them through a variety of methods. So here we've got some internal nanotubes that fuse and make a little single compartment on the inside. Or you can see an example of this kind of GUV going a bit crazy and forming these discocyte-like structures and bending and twisting and then refusing and then incorporating some of the exterior solution into its interior as well. And just to please review number 2, that didn't believe topological transitions in 2D based on our confocal imaging. Again, we have some fantastic facilities here in Leeds, so we could go do some lattice light sheet microscopy and show these events in 3D as well. And finally, this kind of re-equilibrates by this kind of formation of buds at the very end of this process. And apart from leakage, we can quantify all these events, but apart from leakage, all of these are kind of underestimated based on our plane of imaging. But the idea is, future work, can we actually control one process over the other? Can we control tubulation over fusion? And it's the kind of cubicness of our particles that are essential for these processes to happen. They're very fusogenic. They have a really high surface area, which packs a lot of this curvy lipid within them, and then causes these kind of lifelike events in our GUVs. We also like to look at the interaction of the nanoparticles we make in vitro. So throwing them at actually real cells. And there's been a debate in the literature of, what causes cytotoxicity? Is it the lipid chemistry, the lipid type, or is it actually the internal nanostructure of these? So we kind of try to take a more systematic approach. So we picked 5 different lipids with different functionalities, and then constructed phase diagram nanoparticles. And in some cases, depending on our lipid system, we couldn't even determine an IC50 value to determine toxicity. So just taking, the same kind of nanoparticle, let's say a hexosome, but made up of different lipids, but exactly the same curvature, we saw very different cytotoxicities, which made us think it's actually the lipid chemistry that's a determining factor for these interactions with the cells. But then we thought, okay, cool, these are great, right? They're not toxic, perfect. They'll be a perfect drug delivery vehicle. But then when we looked at kind of the uptake of these nanoparticles using kind kind of confocal microscopy, but also flow cytometry, we actually saw that the particles that appeared non-toxic was actually because the cells didn't really take them up, at least for the time frame of our experiments. So we kind of developed this performance metric which relates these kind of IC50 values to the cell uptake of our different nanoparticles as well. So, it's great if they're not toxic, but they really need to enter a cell and carry out their function, right? So we need a bit of a balance of both. You might also remember not long ago during the pandemic, lipid nanoparticles saved our lives. So a lot of the kind of vaccines for COVID were lipid nanoparticle based. But it's really quite shocking because actually it's only 1% of this nucleic acid cargo in the LNPs that functionally gets delivered to the cell. And this opens up huge potential for kind of formulation improvement and potency and so on. So we've got some grants with AstraZeneca, and Bin Yang is the kind of lead from AZ here, and we're at ISIS doing some sounds experiments where we try and understand how kind of the structure of lipids, but also the nucleic acid structure as well, affects biological performance. But we also do a lot of stuff in the lab in the group to try and improve the formulation, because one of the key limitations of these nanoparticles is for them to escape the endosome and release the cargo. And it's actually the formation of this curved lipid structures that are thought to be essential in order to fuse and deliver into the cell. And again, we also try and improve stability, because you might remember they had to be stored at -80, and it's not fantastic for developing countries, for example. We can also do some kind of chemistry and functionalize the surface of these nanoparticles. So here we took a cubosome and did some click chemistry and attached this affimer. So this is a synthetic antibody, which kind of targeted some overexpressed receptors in colorectal cancer cells. And we also loaded it with an anti-cancer drug. And if you can see here, kind of the survival rate of the mice that got this treatment, the tagged cubosomes, our mice pretty much were happy and survived compared to the control or non-targeted group. And also, they very much, if we looked at where the drug went, the targeted group very much went to the tumor site rather than the non-targeted group over here. So we can also functionalize the surface. And just finally, just a few more slides. I talked to you about nanoparticles, but we also work with these kind of structures in bulk, but also in 2D as thin films. So I showed you before that we see these structures in nature. They kind of have periodicity of the micron scale. However, in the lab, unfortunately, we can only make them with sizes of about 10 nanometers. And there have been some kind of theoretical predictions saying that actually thermal fluctuations will destroy these structures with lattice parameters above a certain size. And we thought we could address this. So we can use, for example, we can stiffen our membrane by adding things like cholesterol, but also we can electrostatically swell them. And by doing so, we've managed to exceed the kind of limit predicted by theory. And if you look at the water channel diameter of these kind of structures, we can go from what used to be the bog standard 3 nanometers, and now we can systematically tune them up to 25 nanometers, which is quite exciting. And we could then also translate this into thin films, so you might be aware of kind of supported lipid bilayers. But cubic kind of phases aligned on a surface have a variety of applications like electrochemical sensors, fuel cells, and templating and patterning, and they have kind of many advantages. So what we managed to do, again, with some amazing facilities here in Leeds, so Bragg, the Bragg AFM facility, so work we did with Simon Connell and then Parsons. And what we managed to do was align this bicontinuous cubic phase, but quite importantly, this was the only one that presented a square array at the interface. So if you think about applications, square arrays are really important, for example, in lithography and templating, for kind of integrated circuits and data storage. And again, we can use the principles I showed you before to tune these pore sizes. And for some self-assembled systems that are currently on the market, if you wish, the pore size we achieve could have a big increase in, for example, data storage. And just a quick final thing, we like to look at kind of phase transition kinetics using various triggers like high pressure or pH jumps or light. And after many kind of frustrating beam times using some stop flow device at Diamond, I got fed up and I was like, okay, it's not working, I need to build my own one. So I approached Nick Kapoor in McKenge. So together we got a student, Mustafa, brilliant, just became a doctor, jointly funded by the Fluid CDT in Leeds and Diamond, who developed this kind of microfluidic stop flow device. And if you've got expensive things like, I don't know, COVID vaccines, the volume of this is very much minimized. So the whole point is to democratize this kind of kit we develop for the community. So it will soon be available for you to go use at Diamond whenever you want. So again, yeah, thank you very much. I'd like to thank the people that did the work, so Zazie and the newly minted Neve and Mustafa, Dr. Neve and Dr. Mustafa, all my amazing collaborators, people at the synchrotrons and large-scale facilities, and you for listening.
Thank you, Arwen. A great advert for all the facilities in Bragg. Well done. Time for maybe one question, I think, is what we'll go for. There's one up there. We'll go for that one.
Hi there. Fantastic talk. I was just wondering, have you investigated how cancer-associated fibroblasts affect the delivery of the lipid and the nanoparticles to the tumour microenvironment?
Sorry, did you say how fibroblasts affect?
Yeah, cancer-associated fibroblasts.
No, we haven't, but we've looked at, we've done obviously, kind of 2D cell culture, we've done 3D spheroids, we've done kind of animal models, and they seem to go in based on the data we have. And these were kind of breast cancer, kind of, or colorectal cancer cell lines, but we've also looked at brain as well. And yeah, they seem to go in and have an effect based on our data, yeah. But not specifically on fibroblasts, yeah.
Great. Okay, I think we'll move on just in view of time. Yeah. But Arwen and of course Joao and others are here and during poster time, so you can grab them then. So our last speaker before the poster session is Chiara Curiale. Good. So Chiara is a visiting PhD student from the University of Palermo, so here for 1 year only, and is working on organ-on-chip platforms with scaffolds and sensors. And today you're going to talk to us about electrospun PLA membranes with random and aligned fibers. There's a long title, so away you go.
Thank you. Okay, so good afternoon, everyone. I'm Chiara Curiale, and I'm glad to be here. I'm a PhD student from University of Palermo in Italy, and I'm here as visiting researcher. And today, I'm here to present our research on electrospun PLA membranes with random and aligned fibers as tunable scaffold for endothelial and endometrial cell culture. So we want to explore basically if the alignment of the fibers can affect cell-specific responses. But let me explain first what a scaffold is. So a scaffold is a 3D structure that mimics the environment where cells grow and proliferate. So a good scaffold has to have a right 3D structure and biocompatible for permit that cells grows and stay stable on it, and also porosity for the flow oxygen and nutrients, and of course also bio-responsive. So in this study, we target two specific tissues that are the endometrium tissue and endothelium. So for endometrium, we use the inner uterus lining tissue for its highly organized architecture and critical for fertility. And specifically, we use the Ishikawa cells. And for endothelium type of tissue, it is essential for gas and nutrient exchange. And for this type of study, we use the UVEC cells, which is the human umbilical vein endothelial cell line. So the critical aspect that regards 3D scaffold is the fact that current 2D cultures lack the native 3D environment where cells are, because we perform usually cell culture on flat and plastic dishes. They are not replicating, they are not so close to what is inside the human body, like physiologically response. So our hypothesis and the question that we want to discover it is if we produce fiber alignment scaffold, and if they can modulate cell types responses. And another question is if one single scaffold can be adapted to different cell types condition. So for the fabrication method, we use a very specific electrospinning setup, and we choose as material a polymer solution, which is a PLA, so polylactic acid. It's very used in biomedical environment because it's very biocompatible and biodegradable. In fact, we can control the degradation rate during the cell culture. So basically, we can understand how much time this material, like this scaffold, support the cell culture in itself. So here are written the most critical parameters, like the voltage applied, the feed rate, and the collector diameter in this setup. But the most important parameter, the critical parameter, is the rotation speed. That is completely changed the shapes and the collection of the fiber. So if we choose 300 RPM, we could have aligned nanofibers or 10 RPM random fibers. So at the end of the process, we can obtain a sheet of membrane that is basically 30 by 22 centimeters. And this is so like how this appears at the end. So we can cut it or modeling regarding of our cell culture need. So once we obtain the membrane, so the whole sheet of the membrane, we cut it and we put inside some PMMA discs. PMMA is a polymethyl methacrylate material, which is basically provide support to our scaffold. So at the end, we obtain a static insert device, which is made of this disc of PMMA, so transparent and rigid polymer, with the inside our membrane that can be like random with random fiber or aligned fiber. So in this case, the advantage is that we have a high throughput method because from one sheet of membrane we can produce a lot of scaffold that are identical, so we can perform multiple experiments in the same time. So with this setup, we can create this static insert. So we obtain the cell chamber in which we can make the cell suspension of Ishikawa cells or UVEC cells, and then we cultivate them for 7 days. So to understand what happens at the biological level, we perform immunofluorescence microscopy, and to understand how the cells grow and attach to the substrate and how the cytoskeleton appears. So here are shown the UVEC cells images. And we can say that if we see the random fibers, the nucleo and the cytoskeleton appears good, and the cells like follow the fibers of the membrane, and specifically for the line fibers, because in the line fibers we can see that the cytoskeletons follow the stress of the line of the fiber, but in the end we can say that UVEC cells morphologically respond in both substrates very well. Instead, for Ishikawa cells, they act differently, because in random fibers the nuclei appears but very randomic and very confusing in the substrate, and we can very see the difference also in the amount of cells that are from the random fiber instead of the line fiber, because this makes more biological sense, because they really prefer a direction in the substrate that is really mimic the native endometrial environment. So the Ishikawa cells at the end, they prefer more aligned fibers. And this is also confirmed by our cell viability data, because they show that we have data that are like more than 85% of cell viability. So this demonstrates that our material, so our scaffold, so this is a PLA, polylactic acid, is optimal for growing both endometrial and endothelial cells. And if we see about the shapes, we can see that UVEC are stable in the both configurations, so both in random and aligned topography, instead of Ishikawa cells that they really prefer the aligned fibers. But at the end, we can demonstrate that this electrospan PLA membrane, so this scaffold, this can be a versatile platform for cultivating different cell types and for different tissue engineering application. Of course, we can use the same material, but with different conditions, and we need to consider the cell type, of course. Moving forward, our next thought about these experiments, we want to perform a co-culture experiment. So we want to add one layer of complexity, layer by layer, to, for example, to see how in the same substrate, two different cell lines can be stable or what. Maybe an idea is to have one sheet of randomic layer and the opposite align and cultivate it both. And another next experiment can be like introducing dynamic flow conditions for introducing more stress and more physiological conditions, also like a mechanical stimuli. Okay, so I want to thank my supervisor here at the University of Leeds, the Professor Virginia Pensabene, and my supervisor in Palermo, which is the Professor Vincenzo Lacaruba and Dr. Francesco Lopresti, where the membrane and the insert were performed, and all my research team for their support and their collaboration. So thanks for your attention, and I'm happy to take any question.
Thank you. So, time for a question or two. There's one right at the back.
Very interesting talk on how you use electrospinning to make a 3D scaffold. I'm just wondering how thick is your aligned fibers, and how do you make sure that the cells are living on the fibers 2D rather than 3D? No, 3D rather than 2D.
Okay, I understand just the first question, so I reply to the first, and then I ask you, please, the second one. So here are shown like the distribution of the diameter of the fibers, which is like sub-micrometric fibers. And these are...
So for the scaffold, the whole scaffold, how thick is the whole macro scaffold?
Okay, so just a sheet of the membrane.
All right. So is any suggestion how you make this aligned fiber sheet into a 3D scaffold?
Okay, so the thickness of the sheet, like of all the membrane, is around like 500 micrometers.
Right.
And so we then perform some images to understand the porosity of the scaffold and also the distribution, the macroscopic distribution of the fibers.
Okay, right. Thank you.
And the next question, can you repeat?
So the last question was about whether you can be sure that the cells are forming a sort of 3D structure within the scaffold, or whether they're just 2D layered on top.
Okay, thank you. So to reply to the second question is that when we perform SEM images or also immunofluorescence images, if we move towards different planes, so towards the Z direction, we can see that cells are attached in different. So for this reason also it's not very easy to take these images because you can really see that they are attached in different planes, like on the Z direction.
Okay, I understand. Thank you very much. One suggestion is that you could use confocal microscopy and do the Z-stack mode. There's a Z-stack mode in the confocal microscopy, and you can look at the 3D illustration of your cells. Right, thank you very much.
Thank you.
Okay. One quick one there, and then we'll move on. So,
why would cells want an aligned structure? Is it some tightly defined roughness or something? Why would cells like to form on a well-aligned structure? Is it implying they need a tightly defined surface roughness to grow on, or?
Can you repeat, please? Because I don't understand very well.
So the question is, why do some cells like the aligned structure and other ones like the more?
Okay. Just because we understand that they are trying to replicate what is in the real physiological environment. So, for example, in the endometrial environment, there is a really a structure with a lot of direction. So the cells prefer to remain to follow this path. Instead, for example, the UVEC cells that are the cells that are found in the vein, they live well, they grow well. So of course, when they follow a line path, they try to attach to these fibers so they live better. But in this case, we don't see so much difference between randomic and aligned fibers. So we can see that they just prefer like both architecture. So it's really depends on the cell type and what is real in the real tissue in the physiological condition.
Thank you, Chiara.
Thank you.
Thank you. And it looks like Claire wants to say something. So,
yeah, give me the mic. Thank you, everybody, for the amazing talks in these last two sessions. You'll be pleased to hear that there's some drinks in the refectory, so please head back over there to have a look at the posters. Don't forget to vote for the posters. have a few drinks. That's on till 6 o'clock this evening. And also just a reminder, please do the membership feedback survey form at some point. The QR code will reappear on the slides tomorrow. Thank you very much.